is here at least? Yeah.
Jonas,
Yes, I'm here.
Okay, good. So did you try before your presentation?
Yes, I did.
Oh,
Okay.
should be okay.
But I can.
Yeah. But we are ready to
Yeah.
start. I think I would suggest we
Ready
start.
to start.
Yeah. We
Good.
can start. It's good.
Okay. So I just want to say good morning, and I'm chairing Svetlana Kodachigova, chairing this session, and we start from the talk by Dr. Prasanna, and please. And it's 25 minutes each talk, so I will inform you when it's time.
Okay, so shall I begin?
Yeah.
Okay. So I'll begin by thanking the organizers for giving me an opportunity to present our work in this workshop. So my name is Prasanna, and I recently joined a newly founded research institute in India named TCG Crest. We are from this department, Center for Quantum Engineering Research and Education. So the main focus of the department is research on the emerging field of quantum science and technologies. I'll discuss more about this towards the end of this talk, where I'll briefly touch upon the relevance of quantum computing in exploring fundamental physics using molecules. But yeah, I'll discuss it towards the end of the talk. So these are the collaborators with whom we have worked on trying to probe the electric dipole moment of the electron, which I'll hereafter abbreviate as EEDM using radioactive molecules. So I'll begin by introducing the EEDM and then motivate it. Then how to determine EEDM using molecules, because this is a property of the electron, and then what's the role of molecular theory here. Then, of course, we will look at proposing radioactive molecules as promising candidates, take a look at some of the results, and then conclude and discuss the future prospects. The first two parts of the talk, I'll go a bit fast because it's an expert audience, and also most of these topics have already been introduced in the workshop in the previous talks. So the EEDM is an intrinsic property of the electron, just like its mass or spin, except that it's not been observed yet. It's exotic because it arises due to the simultaneous violations of parity and time reversal symmetries in the theory that describes it. So if this property is detected, then it's a direct observation of T violation. It's also an excellent probe of CP violation beyond the standard model of particle physics. So this has been discussed in great depth in many talks, for example, the one by Professor Reeves. And it also can provide insights into the matter-antimatter asymmetry problem in the universe. So now that we know what the EEDM is and why it's useful, then the next question is, how do we measure it? So of course, we can't use an electron directly to measure it because it's charged and it will accelerate away, and you get too little a coherence time for the kind of precision that you really want. So we use atoms or molecules as proxies. In this talk, I'll be focusing only on molecules. So delta E with a subscript M refers to the shift in energy in a molecule that's appropriately chosen in an appropriate state, but due to each of its electrons possessing an EEDM. So the quantity that accompanies the EDM, that is dE, is one that has units of electric field. So here I've again split it into two parts: an effective electric field, which is only possible to calculate using theory. So this quantity cannot be measured. The polarizing factor, which was again introduced and discussed in detail in previous talks. So this is between 0 and 1, and it depends on the molecular dipole moment itself, the external electric field that one applies in an experiment, as well as quantities such as the rotational constants. So this can be calculated or measured. This can only be calculated using relativistic many-body theory, because this is a purely relativistic effect, and this is only measured in experiments. So this requires a combination of theory and experiment to then set bounds on dE. So the quantity E effective itself can be calculated using this expression. This arises when we take dE as a perturbation to the electromagnetic interactions in the Hamiltonian. And this is basically then the first order shift in energy, psi being the unperturbed wave function of the molecule. This operator is the EDM operator, which I'll refer to as HEEDM in the subsequent slides. But this is basically just a D dot E in disguise, because this is the 4x4 version of the polymatrices. This beta basically ensures that we are in relativistic domain, and EI internal is the internal electric field that's experienced by the ith electron in the molecule due to the other electrons and nuclei in the molecule. Now, this is an internal electric field, so it takes the form of a gradient of a potential. One of whose terms would contain a two-body term because of the electron-electron interaction. So rather than use this, it's computationally more efficient to use the one-body effective EDM operator for our calculations. Of course, this too was again discussed in previous talks, but this is what is often used because it's so much easier to use this in computations. So now that we know how to calculate E effective, of course, the biggest challenge being that you work with heavy molecules. In the context of this workshop, we work with radioactive molecules. It makes life harder, of course, because it's much more computation. And also because it's a relativistic property, we use relativistic many-body theory. So this is very, very compute intensive, and most of the challenges lie here. But before we get to the question of why radioactive molecules are interesting in the current scenario, and discuss some of our results and the theoretical challenges, we'll first look at the statistical sensitivity of an EDM experiment. Of course, this too was explored in great detail in the earlier talk. So I'll just state that it depends on the number of molecules that you can produce per second in your experiment, the coherence time that's available to you in the experiment. So I'm just assuming that this is a beam experiment scenario. It has the polarizing factor, and the E effective, the quantity that we have been discussing till now, that occurs outside the square root, unlike n and tau. So one case would be where you choose a molecule with a reasonable value of E effective, and then you try to improve n and tau. Then the other case would be to choose a molecule which has a reasonable n and tau, but which has a very large E effective. And because this comes outside the square root, this helps a lot in improving the sensitivity in the experiment. So we are often interested in molecules which have larger values of E effective. And since there is a heuristic that tells us that, okay, if Z is the atomic number of the heavier atom, then you expect a Z cubed kind of an enhancement. We would be interested in exploring heavier and heavier systems, and that's basically where radioactive elements as well as super heavy elements all come in. There are, of course, other considerations. It's not so simple because almost always all of these are not satisfied. But besides that, there is no way of knowing beforehand what the E effective of a molecule will be. So to a reasonable extent, to a very good extent, we have to actually rely upon the previous works in literature, borrow wisdom from them. And of course, the Z-cube heuristic that I mentioned earlier. And we also have to take into account the many-body effects that lie beyond the mean field approximation. So the mean field approximation in this case would be the Dirac-Hartree-Fock approximation. And whatever physical effects lie beyond it, we use the word electron correlation to describe it. So there are cases that we would encounter where electron correlation effects become very pronounced, and then the calculations become very challenging in that case. So this is also one of the things we take into account. Of course, there's not much of a way of knowing beforehand what to expect. The last point is more practical in nature, how compute intensive the system is, because you deal with heavy systems and you do relativistic calculations. We always have to be aware of things like how sensitive are our results to the single particle basis sets we choose. If at all we need to do all electron calculations or freeze some of the electrons, where to cut off virtuals, and so on and so forth. So at this point, before we go to radioactive systems, I'll just briefly, I'll just state again that molecules are excellent non-accelerator probes of very large energy scales. And just for comparison, I've given LHC as being around 10 TeV. So now we'll go back to determining the wave function, because that forms such an important part of evaluating the effective electric field. So of course, we use a relativistic many-body theory, but in our works, we choose the relativistic couple cluster method, or what I'll abbreviate as RCCM. Just to be more clear on the word relativistic, we use the 4-component Dirac-Coulomb Hamiltonian for our calculations. So the couple cluster method basically builds upon the Dirac-Hartree-Fock wave function. A non-unitary operator E par T acts on the reference state phi naught, and this generates all the particle hole excitations, and therefore all the many-body effects beyond Dirac-Fock, or the electron correlations. Now, if you look at it this way, where each T1, T2 up to Tn, each describes their own particle hole excitations, then you could view psi as a linear combination of determinants, but each one of them being entangled. So I'm just taking this viewpoint of looking at the wave function, so that when we again get to the quantum computing part, I can comment a bit on the importance of entanglement in these calculations. So in that sense, if you take a heavy molecule, it can be viewed as it could be a highly entangled quantum many-body system. Now, coming back to the couple cluster method itself, we choose this because it's identified, it's known to be the gold standard of electronic structure calculations. This is because of some very nice features that it possesses. For example, theoretically, it's very desirable to have a theory that's size extensive and size consistent, even when it is truncated at some particle hole excitation level. So couple cluster theory has that feature. Excuse me. And it's also an all-order theory in the sense that it treats the residual Coulomb interaction to all orders in perturbation at a given particle hole excitation. Sorry. So that's basically a very brief introduction to the couple cluster method. That's about getting the wave function. But once you get the wave function, then you have to evaluate the properties. So you could do it in two ways. I'm just restating here that we can take the EDM as a perturbation to the molecular Hamiltonian with electromagnetic interactions. The lambda here would be your DE. So the expectation value approach basically involves taking the expectation value of the EDM Hamiltonian that we saw in the earlier slides with respect to the unperturbed molecular wave function. So in a non-trivial step, in a non-trivial series of steps, you can show that this reduces to this particular expression. The C just tells us that each of the terms in the expression is fully connected or linked. And one immediately notices that there's an EPA T dagger and not an EPA minus T here. So it's really an infinite series, and it's a non-truncating series. So you have to terminate it somewhere manually. So we are left with two options. Either we can only take the terms that are linear in T. I call this the LECC approach, or the linear expectation value couple cluster approach. Of course, we solve the full couple cluster equation. So we don't solve the linear couple cluster, but rather the full CCSD equations, for example, but do this approximation only at the level of an expectation value. That would be one route. The other is to, of course, try to evaluate as many terms as possible. So I just called it the nonlinear expectation value couple cluster method. But of course, we need to know where to terminate, and this would already involve too many terms or too many diagrams. So we need to find some way of programming this. So we use the intermediate diagram approach to do this. And we also extensively parallelized it so that we keep the computation under control. I've just expanded this into the first couple of terms here. This would, of course, translate to your Dirac-Fock contribution itself. So, and this would be the HEEDM T1 term. I've just put it in a different color because this turns out to be the most important correlation effect that comes when you calculate E effective and so on. So we'll come back to this when we discuss the results, but I just thought I could mention it here and set it up at this stage. The other approach, instead of evaluating the expectation value in the couple cluster framework and dealing with truncation and all that, is to just go to an energy derivative approach. Here we go for the numerical variant of it called the finite field couple cluster method. So we tried, of course, all three. So in the beginning, we used to work with the linear expectation value approximation because that was really comfortable in terms of computation. And it did turn out to be a very good approximation when we later went for the nonlinear version and also the finite field approach. This is particularly advantageous because the couple cluster energy does not have the same problem that these properties have. So the energy naturally terminates very quickly. So it's possible to easily evaluate it in the couple cluster framework. So having made this comment on the couple cluster method and how to evaluate properties using the method, we'll quickly see why radioactive molecules are interesting for us. Of course, we expect a very large effective electric field, at least in some of the molecules. I'll tell why I say certain molecules when we go to the results. But of course, on the experimental side, it's very challenging because it's hard to produce a large number of molecules per second, and coherence time is going to be a problem. There was very scarce literature, but this was until recently. So now in the last few years, there's been tremendous progress, some of which was discussed in this workshop itself. And as Professor Ronald says, there's a bright future ahead for radioactive molecules with all these facilities working on them. So now it's a good time to actually think about both not just radioactive systems, but also go one step ahead and look at molecules with a super heavy atom in them. So this is really a promising direction to now pursue. So before I really get to the radioactive systems, I'll discuss a heavy system, that is diatomic molecules, with mercury being the heavier one. And we'll just try to understand what really happens here, and then see if we can really use this knowledge for the radioactive systems when we go there. The answer is no, because it's really, really unpredictable. So one of the main reasons why I'm showing these slides are to just show how unpredictable the theoretical calculations can be. So when we carry out surveys or when we try to explore possibilities of finding new candidates, it's almost always done on a case-to-case basis. And it's not too often that you see neat trends that that make us predict things beforehand clearly. So I've just given mercury halides and mercury alkalis as two examples. Both of them contain mercury as the heavy atom, but the other atom in the diatomic is either a halogen, or in this case, they are these alkali atoms. So just to give a feel for numbers, mercury halides have effective electric fields that are over 100 GeV per centimeter. Thorium monoxide is 75, so this is already like 1.5 times larger. And the second and third leading candidates, HFF plus and YBF, they have effective electric fields that are like 23 GeV per centimeter. So these are already 5 times more than that. In this talk, I'll only be focusing on effective electric fields, not on the scalar pseudoscalar interaction or other properties like the dipole moments in the interest of time. But this already tells us a lot about how hard theoretical calculations can get. So the one in blue is your Dirac-Fock calculations. You see there's a trend here that shows that the Dirac-Fock values decrease gradually though. And then the correlation effects account for something like 10%. And we tried all 3 approaches here, a linear expectation value, the nonlinear one, as well as the finite field approach. And we see that they agreed to a reasonable extent, but then there is some error depending on what approximation you make, even within a method. There are other errors that you can see, which I mentioned in the last line. So of course, error estimates depend on the system, right? If you use a system that's lighter, and then you can probably have more control on the errors, probably. And with heavier systems, usually things become harder. So for HGX, for example, if we take into account all the things like the single particle basis or the sensitivity to bond lengths, I'll get to the bond angles part when I discuss polyatomics. The sort of error that can come from ignoring triples and so on. So the error was estimated to be somewhere around 15% in these calculations. Now, if you just replace the halogens with an alkali, we would still expect that we get reasonable results, but of course we would be optimistic about being able to produce more alkalis, but here things go really wrong. So the effective electric field drops drastically from 100 to just 12 at the Dirac-Fock level. That's the first problem we already see. And the second problem is that the correlation effects are very pronounced. So we have to be very careful in carrying out these calculations, and we have to do a whole lot of tests to make sure that the results we get are already reliable. It's only later with hindsight that we found out that this sort of a behavior comes because the unpaired electron in the singly occupied molecular orbital that localizes on the alkali instead of the heavier mercury atom. But again, there was no way of knowing this beforehand. So these surveys were really necessary at that point. The important things to notice as a theoretician when we try to understand what's going on with the trends, with the Dirac-Fock contribution, we usually look at the SP half mixing, which I'll just call hybridization in this talk for ease of just mentioning it. It basically occurs when you rewrite the effective electric field this way. Of course, there's large and small component mixing because of HEDM. And here K and L can be S and P half. And then this is what I refer to as the SP half mixing. And this turns out to be the most dominant contribution in these kind of systems, usually. SP half mixing, again, is dominated by the heavier atom, not by the lighter one. But when we go to radium-based systems, we'll see that there's a slightly different trend that we can also observe. And if you recall the HEDM T1 term that we saw earlier in the expectation value expression, this is what almost always dominates in correlation terms. In fact, we found that here the OT1 contribution or the HEDM T1 contribution was more than twice the Dirac-Fock value here. So, and this usually dominates. If we try to understand further where this comes from, then we see that it comes because of important correlation effects such as the Bruckner pair correlation. Of course, the problem with couple cluster being that it's an all-order theory. So as it's advantageous, but at the same time, a lot of physics is swept under the rug. So we need to often make connections with many body perturbation theory to see what sort of effects lead to each of these correlation terms. So this sort of broadly gives a picture of what happens in diatomics. I'll not be discussing triatomics in today's radioactive species, but I just thought I could briefly mention. So YBOH, for example, is a linear geometry. But when you go to bend geometries, where I replace mercury fluoride with OH, we see that the behavior completely changes. So Professor Hertzler made a quick reference to this in his talk, but you would really not see that the effective electric field of mercury oxide is around 100, but it rather drops to just 28, just by the virtue of the system being bent and so on. Also, it's very unclear what the progression trend is, by which I mean that if you go from HGF to HGOH to HGCH3, for example, the effective electric field values do swing, but these are still in the very initial stages. So of course, a lot of study have to be done on this front, but I just thought I could mention this so that we get a picture of what sort of challenges we normally face in theory. So now when we move over to the radioactive species, we'll first begin with radium hydride. Radium fluoride is, of course, a well-known candidate in EDM experiments. So we did try out hydrates because it's known that hydrates usually have a larger effective electric field. The bonus that we had here really was that the dipole moment was also very large and comparable with radium fluoride, the molecular dipole moment, which is often not the case when you go over from a fluoride to hydride. But of course, unless and until we find ways of doing a trap experiment, we would run into issues with the polarizing field because of the hydrogen atom being here. Then we'll move on to the radium halides. So we saw mercury halides earlier. So we'll just take a look at the radium halides, and you already see that the Dirac-Fock trend itself is different. So earlier it was monotonically decreasing with an atomic number of 80, but when you go to 88, when you go to radium, that is, it already starts increasing. The correlation effects are, of course, more pronounced than that in mercury halides. Now we make a substitution. Instead of halides, we look at copper, silver, and gold. And we see that the trend again changes. So if we just try to understand why this happens, of course, the effective electric fields are large here. The correlation behavior changes here, but I'll not be focusing so much on this part, although one could do similar analysis for the correlation effects. But if you see what happens at the Dirac-Fock level, you see that the SPR of hybridization from Ra, that is if both S and P have come from the heavier atom, that increases from fluorine to astatine. And if you look at the contribution from the lighter atom, well, supposedly lighter because astatine now becomes heavier than radium. But if you look at it from the halogen atom, then it increases and it's also positive. So this trend increases overall. But if you look at the radium, copper, silver, and gold, both the things change. That is, the SPR hybridization no longer follows a monotonically increasing trend, but rather it's just constant. So that already works against us. And the other thing is that the contribution from the Y atom increases, and it's also of the opposite sign. So therefore, the net Dirac-Fock value drops. So like I said earlier, a very similar analysis can also be carried out for the correlation terms. But of course, the idea was to just give a flavor of what goes on here. Now we'll finally look at the results from LRX, that is LRO, LRF plus, and LRH plus. These are super heavy systems. And of course, recent work was done on LRO by Professor Berger's group. And just a few days back, there was also a work by Professor Langcheng's group on LRO. Here we also do LRO and then two other systems, LRF plus and LRH plus. The first challenge that we right away get in these sort of super heavy systems is that LR has a different electronic configuration in a relativistic treatment already. So, and of course it's very heavy, and then these sort of super heavy systems come with their own theoretical challenges. So we first obtained the potential energy curves for all these systems, and then we calculated the effective electric field as well as other properties. Since there is no clear trend here in terms of halogen or something, I've just put a bar chart here. This still gives a good idea about the sort of effective electric fields we have. It's tremendously enhanced in super heavy systems. So from 100 in mercury or from 70 in radium, you already jump to 200 or 300 in these super heavy systems. And the correlation effects can also be quite dominant, as in LRH plus, where you go from something like 270 or 280 to close to 350. This we are working with Professor Ronald and also Professor Sato and Professor Sakemi. So of course, like Professor Ronald also said in the first talk of this workshop, there's always work between, there's close collaboration between theoreticians and experimentalists in proposing new candidates. So here we are also working on trying to find out what sort of N and tau we would expect and what sort of scheme we would have for these sort of experiments. With this, I'll just conclude with some ongoing and future work. So of course, radioactive molecules are very promising. So there are two directions in theory that we can go in. One is work on the many body front and work with better and better theories, because if you're going to deal with systems like mercury alkalis or even super heavy systems, it's always good to have a better theoretical framework to begin with. On that front, we plan on working with what's called the normal couple cluster method, where the Bra and the Ket are treated on not on an equal footing, but on a different footing. This sort of a structure ensures that the expectation value terminates, so we don't have to deal with the truncation problem. A better dream would be to, of course, work on the extended couple cluster method, where this is generalized even further to an exponential of -t. In the long run, we also would like to explore multi-reference couple cluster methods in the context of exploring fundamental physics. And of course, on the other side, we have to search for new candidates. So keeping in mind the experience we gained from working on triatomics with mercury and so on, we would like to explore further triatomics and polyatomics containing radioactive atoms, specifically super heavy systems for future works. The last topic that I'll discuss is new directions, completely going in a different direction, which is trying to use quantum computers instead of classical computers. So we saw that psi is entangled, and molecular systems, therefore, we could think of as being well suited for quantum computing. And indeed, quantum algorithms exist and have they predict that you would get an exponential speed up in time complexity when you work with quantum computers, or in other words, get a quantum advantage over classical machines. So of course, it's in its infancy, this entire field. So we have very few qubits, so we can work with very, very light systems with very low quality basis sets. So we have carried out some pilot studies on calculating just atomic energies at this point to assess precision. The algorithm we used is a quantum classical hybrid algorithm called the VQE algorithm. So we have submitted this work very recently. We have also extended our calculations to the relativistic framework and have gone beyond energy. And we have also tried to calculate hyperfine structure constants and highly charged ions. So this work is still this work is ongoing and the manuscript is under preparation. So in the future, we plan to include multi-configurational effects appropriately in these sort of calculations. And hopefully in the next few years, when many, many more qubits become available, like IBM or Pascal predicts if there are 1,000 odd qubits, then we can really start thinking in the very near term about using quantum computers for probing fundamental physics. So with this, I'll conclude by just showing a chart of where the field stands and where how far the field has traveled. And the hope is that with radioactive molecules, we will be able to constrain beyond standard model theories much better and also hopefully be able to shed light on the baryon asymmetry problem. So with this, I'll thank you. Yeah, thank you.
Thank you very much. So any question? So we don't have, okay. So Timur, please.
Yes, I have a question about your results on mercury hydroxide.
Okay.
Yes, and yes. So your result look really very interesting. So it violates any intuitive, so to say, expectations, right? So
yeah,
because one would expect, of course, that it has to be very similar to mercury fluoride. Do you have some explanation for such a huge difference?
At this point, we can only look at the geometry because, for example, when you look at YBOH and YBF, because YBOH is linear, it's probably why the effective electric fields are comparable. And in fact, we did consider a hypothetical HGOH geometry, which is linear, and then we saw that it did really agree with HGF. But the problem is the ground state of HGOH is bent, and it's actually quite bent. I mean, the bending angle is something like 104 degrees or something, and I think that's probably what messed up our estimates for the effective electric field. But the best we could do was go back and look at the SPF mixing, and again, because the Hartree-Fock was the dominant contribution, and there we already saw that it dropped drastically. So perhaps the energy denominator or the overlap integrals in the numerator really don't work in our favor, because if you want to go beyond the SP half explanation and see what really happens, then one possible way to look at it is by seeing whether the energy denominator or the overlap integral in the numerator for the radial overlap works in our favor, and it probably didn't. But yeah, this we have to, of course, work further to see what's really going on in this sort of a system.
Yeah, if you have different degree of SP hybridization, it means that it looks like there is a crossing of levels, right? So you just have different electronic state for case of mercury OH. And
yeah.
So it's not anymore, so to say, sigma orbital. We understand that in band system it's not sigma, but next to mercury it looks like this is not sigma. Oh, it's very interesting. Thank you.
Thank you. Thank you.
So there is someone else. Ronald, please.
Yeah, thank you. Nice talk. So I wanted to hear a bit more about this quantum computing. So what's the status of the field and what are the expectations? So is more work going on in parallel, or?
Yeah. I mean, it's a relatively new field, and it's been picking up in the recent times. So probably in the last 3 or 4 years, it's really started moving very, very fast. So people have started doing quantum chemistry or atomico-molecular calculations using quantum computers. But currently, what limits us is the number of qubits and also the quality of the current available hardware. So it's called the noisy era, what we live in. So we work with a lot of noise when we go to real quantum machines, and also the qubits are limited. So at this point, if we use something like a couple cluster method, then we are limited to about 20 or 25 qubits at most, because even that starts becoming very expensive very fast. But the hope is in the next few years, if the qubits increase, then we can start also incorporating error correction strategies. So it should help in also controlling the error. And the fact that number of qubits have increased will allow us to work with larger systems, because the number of qubits basically reflects the number of spin orbitals that we include in a calculation.
Mm-hmm. So I would like to ask you, you described at the beginning of your talk very interesting method based on Dirac-Fock basis functions. Did you try to calculate, for example, ytterbium OH using this method? And maybe it's possible to compare with other kind of calculations recently published by Davis et al.
I'm sorry, I couldn't hear your last couple of sentences.
No, I'm saying that did you try to calculate ytterbium OH using your method?
At this point, we only calculated ytterbium hydroxide using the linear expectation value approximation. But of course, it should be very much possible to do it by either using the energy derivative or the nonlinear version. But we didn't go for it because we didn't expect to see such a large difference. I mean, YBOH is one of those well-behaved systems, so we didn't really explore it too much in that direction.
Yeah, it's interesting. Also, it's a function of like angle, maybe geometry, different kind of geometries also would be nice to explore, right?
Yeah, the problem, YBOH is linear, but if you go to a bent system like mercury hydroxide or any other bent system, the first problem we'll run into in terms of practical issues is the computation, because the molecule is no longer going to be as symmetric as it was earlier. So for example, when we work with linear systems, we can say use the C8 point group symmetry or something that really works in our favor. But once the molecule becomes bent, then it has much reduced symmetry. So that would mean we calculate many more matrix elements and things become very expensive.
Much more difficult. Yeah. Okay.
So that's a problem that we currently are stuck with. So we have to figure out a way to handle that at this stage.
So any other questions? We still have very few minutes.
Did I finish my talk too fast?
Oh no, it's okay. It's just a last day. People already kind of maybe have to do something else and so on. Yes. We have one more question. Matt Grohl.
Can I ask some more detail about the Lorentzium calculation?
Yeah, sure. By more details, are you asking about the computational details, like the basis sets we used and so on?
No, so these electric fields seem very high compared to what I'd expect from, like, comparing to the previous row of elements and like the Z cube scaling. Do you have any like qualitative reasoning for why they have such large electric fields?
I mean, it's just a known heuristic that the larger your Z, you would expect a better enhancement. And also we again just go back to the SPF mixing and then see that. So basically, when you describe it using the couple cluster approach or even at the Dirac-Fock level, most of these numbers are decided by also cancellations. It's not just about the Z being high alone, but then we also deal with a lot of cancellations. So for example, if you look at LRO, and LRH plus, the Dirac-Fock values are not all that drastically different. This is something like 240 and this is something like 270. But if you look at the final results that we get, this still is stuck at 260 while this skyrockets all the way to about 340 or something. So this particular behavior is attributed to the fact that the HEDM T1 contribution is not cancelled out so much, but here there are other correlation effects that end up cancelling out most of OT1. So one is the Z cubed heuristic, the other is the kind of cancellation mechanisms that are at play, and that really becomes system dependent.
Okay, so we can now invite next speaker. It's Jonas Karten, please.
Thank you.
Hey, can you see my screen? Can you hear me?
Yeah, it looks nice.
Okay, yeah. So thank you very much, and thank you very much to the organizers to giving me this chance to present our new upcoming experiment here in this very nice environment. My name is Jonas Karten. I'm a new postdoc in the MIT Department of Physics in the group of Ronald Garcia-Roos. And today I will talk about symmetry violating properties which we can derive from single molecular ions in a pinning trap. Before I start with my talk, I would like to introduce you to our new collaboration, which consists of these 9 people. It's quite unique because we come from two different backgrounds. The one background is laser spectroscopy on the one hand, David DeMille here, Ronald Garcia-Roos, and Nick Hutzler, which come from spectroscopy of molecules and radioactive molecules. And then on the other hand, we have expertise from mass spectrometry of radioactive isotopes, namely Ryan Ringel, Jens Stilling, and myself. I would also like to highlight our three students, Silvio, Scott, and Parashar, who have been performing a lot of simulations, which I will show in the second half of my talk. Okay, my goal for today is to convince you that merging these two very well-established fields of atomic physics techniques, namely Penning ion traps and lasers, are optimally suited to tackle open nuclear physics challenges, specifically P violation, which we have heard already a little bit about this week. The standard model of particle physics has been very successful in describing and even predicting fundamental properties of elementary particles at many different scales of energy. But as we have heard this week extensively, the model is not perfect as it fails to describe the majority of matter and energy in the universe. But by measuring symmetry violating properties at tiny effects which diverge from the standard model, we can get information about the physics which is not described by the standard model. In our case, we want to study the so-called parity, which describes the symmetry in space. And naively thinking, we would assume that observing elementary particles through a mirror, that physics would be conserved. And this seems to be the case for the electromagnetic and the strong force. However, in 1957, Ms. Wu and colleagues have found out that in the beta decay, which is famously transmitted through the weak interaction, the parity is slightly violated. Following that, we are also trying to study the so-called parity violation, for which the dominant modes in atoms and molecules are shown in this slide. So as you can see, all these effects describe the interaction between the electron shell and the atomic or molecular nucleus here, which is great for us because with lasers, we are very familiar with studying the electron shell to learn about the nucleus. The first effect here on the left side describes the interaction through a Z boson. However, this happens through vector currents at the nucleoside, which means that these effects are nuclear spin independent and they are suppressed in diatomic molecules, so we can ignore this effect for now. The other three effects which are shown here are nuclear spin dependent effects, which are interesting for us, which we can access in our lab. The first effect looks very similar. However, the vector and axial vector currents are swapped. And this interaction happens through a Z boson, which has a very heavy mass, 91 GeV over c squared, which means that this interaction is very short range. So this happens only inside the nucleus, which means that these electrons, you have to penetrate the nucleus, which also means that it happens only in s and p orbitals. The next effect was already described in, for example, the talk of David DeMille, which is the so-called anapole moment, which you can think of as a torus-like current of W and Z bosons, which create a local and circular magnetic field inside the nucleus to which a photon can couple to the electrons. That also means that this effect is suppressed compared to this effect by the fine structure constant alpha due to the additional photon here. However, this effect also scales roughly by Z cube. So in heavy nuclei, this effect is more dominant, whereas in light nuclei, this effect is typically more dominant. The last effect here is very similar to the first effect. However, it also couples to the hyperfine structure, and it's a little bit smaller in magnitude. However, if we measure these effects, we only measure a bulk quantity. So it's very hard for us experimentally to decouple these isotopes, or these effects, which is why we eventually want to bring our experiment to a radioactive ion beam facility, because there we can basically measure different constitutions of neutrons and protons all across the nuclear chart in order to decouple these effects experimentally. So these effects allow us access to the electrorecoupling, for example, which so far has mainly been performed in high energy experiments on electron scattering. These effects also give us access to new bosons, for example, the Z prime boson or dark bosons, which allow us, if we study them at low energy, to access TeV scales of mass. They probably allow us also to say something about the neutron spin distribution, but I put here an exclamation mark because it is still relatively hard to motivate these parity violating effects, which I want to invite all of you to join the panel number 1, where we will discuss exactly this problem. And the reason why these experiments have so far not been done very extensively, actually only in very few atomic systems, the cesium one down here from 97 is probably the most famous one. The reason for that is that these parity violating effects are proportional to the Fermi constant, which is on the order of 10 to the minus 14. So these are very, very tiny effects, which means that we need to perform very high precision experiments, or which means that we need to apply certain experimental tricks in order to amplify these effects. The trick or the tricks which we are using, I would like to go through now. And that can be best described along with this formula, which describes the sensitivity to these parity violating effects by mixing states of opposite parity, even and odd parity. And as you can see, these effects are scaling inversely proportional with a difference in energy between these states of opposite parity. If we would measure an atom, then the parity operator scales with the angular momentum quantum number, which means that the difference in energy is only on the order of 1 electron volt. Whereas if we move to molecules, for example, diatomic molecules, as we are planning to, the parity operator scales with the rotational quantum number, which means that this difference in energy is only on the order of micro electron volts, which give us a natural amplification of these effects in molecules on the order of 10 to the 5, which is already incredible. The next experimental trick which we apply is by putting these molecules into a strong magnetic field. What happens in such a strong magnetic field to states of opposite parity is the following. Due to the Zeeman shift, states of positive parity are pushed up in energy, and states of negative parity are pushed down in energy, which means that at a certain strong magnetic field, these states will come into near degeneracy, which means that this energy difference here becomes even smaller. And this is exactly where we want to perform our measurement. This is an example for a silicon oxide molecule where the strong magnetic field would be about 1.5 Tesla. Next, we want to mix these states of opposite parity. For that, we apply a weak oscillating electric field that induces the so-called Stark mixing. And that allows us to describe these two states within one time-dependent basis, which depends on the one hand on the positive parity state and on the negative parity state. Each of them have a time-dependent amplitude. To make our experiment a little bit easier, we prepare our ions in a specific state, in our case, in the negative parity state. So with lasers, we can deplete all these states of positive parity such that the whole population is only in the negative state. And then what we measure is the population in the positive parity state after some time, which we can fix very precisely in our measurement. We can perform a little bit of math, and what we find out, if you are interested in, you can look it up here in this paper. What we find out is that the positive parity amplitude is only dependent on experimental parameters, such as our measurement time, the frequency of the electric field, the amplitude of the electric field, and the energy difference between these two states here, which is dependent on the magnetic field. And then this W parameter, which gives us direct access to the whole weak interaction with the parity violating effects. So just by measuring basically a counting experiment, how many particles ended up in the positive parity state, we can get direct access here to this weak interaction, which is great because in experimental physics, you always want to convert an experiment into a frequency experiment because computers are great at counting. And the group of David DeMille in their proof of principle experiment showed that applying these experimental tricks, we can gain an enormous amplification factor of 10 to the 11 compared to atomic systems. So let me quickly walk you through the experiment of David DeMille, because that is very similar conceptually compared to our experiment. So first, they're using a superconducting magnet in order to produce this strong magnetic field. Then they are placing a couple of electrodes inside the magnetic field in order to induce this state mixing. Then they have an ablation source, which creates these molecules. In their case, this was barium fluoride in a neutral form. This was a fast beam of many particles flying through their setup. And then at different stages, they have laser interaction zones, which allow us to prepare these isotopes or these particles in the specific parity states. So in an energy or frequency diagram, let's say we have these two states of opposite parity, we put them into the magnetic fields, they come to near degeneracy, then we deplete them such that we can start with our easy starting condition with all particles in one parity state. We let them interact with the electric field to get access to the weak interaction, and then we just measure how many particles ended up in this positive state. In their case, they were using fluorescence spectroscopy. And again, they showed this amazing amplification of 10 to the 11. However, for radioactive particles, this is not the perfect approach, because they are using a fast beam of neutral molecules, which means that their laser interaction times are very, very short, on the order of microseconds here for these in these laser interaction zones. In addition, this setup requires a lot of particles, which is insufficient for the application of radioactive ion beam facilities, because if you go far away from the island of stability, the production rates drop significantly such that you are left with only a couple of particles per hour. And finally, in my opinion, as being a mass spectrometrist, the final state detection can also be improved in our traps, which is at the moment based on fluorescence. So in the next slides, I want to convince you that panning traps are the optimal solution to tackle these points and to bring the setup to a radioactive ion beam facility eventually. So let me introduce you to a panning trap. A panning trap consists of a strong magnetic field, typically of a superconductor, which puts the charged particles on a circular motion. In order to trap the particles in 3 dimensions, axially as well, we overlap the strong magnetic field with a weak electrostatic field. I want to emphasize this is an electrostatic field, not a RF field. And by that, we can trap particles in 3 dimensions. Trapped particles have a very complicated looking motion, but in principle, this is simply a superposition of 3 eigenmotions. They're shown here. There are 2 radial motions and 1 axial motion. And the fact that these are 3 eigenmotions is great, because in a panning trap, the square sum of these 3 eigenmotions is equal to the cyclotron frequency, which is directly proportional to the ion's mass, which is great. And the reason for why these panning traps are so popular in the mass spectrometry community, because by measuring these 3 eigenfrequencies, you directly get access to the mass of the particle. But since we have eigenfrequencies in our trap, we also gain full control over the eigenmotions through resonant excitation. Think about it in a way such that we control electronic states in an atom, where you can excite or de-excite them by resonant excitation with the laser. In our case, we have resonance frequencies of kilohertz or megahertz, so a little bit different frequency regime, but in principle, the principle is the same. So if we apply now radio frequency fields here at our ring electrode, for example, at the big motion here, the mu minus motion, we can decrease the amplitude. So we can cool down our particle motion down to the center if we apply the frequency here at this eigenfrequency. And we can do that in principle to every eigenfrequency to, for example, cool them down to the center of our trap. So in summary, we have very stable and homogeneous electric and magnetic fields. We have full control over the eigenmotion, which is great. And that allows us to achieve very long trapping times for only single particles. And by long, I mean much longer than a second. At CERN, where they perform or where they use these traps to trap antimatter, they actually never lose their particles unintentionally, I would say, because the only way to lose these particles is by collision with rest gas. So if you improve your vacuum inside the trap, you are basically never losing your particles. These traps also have a large mass range, so we can trap anything from electrons up to large molecules, anything from single particles up to large clouds of particles. if we operate or if we design our trap in such a linear fashion, we also get access with lasers along the magnetic field lines here. And that allows us to perform the state controlling, additional laser cooling down to micro Kelvin in principle if we want. And that allows us also in our measurement scheme for a good detection. And another big advantage of these panning traps is that we can live monitor the motion of our particle. So just assume the particle is just having an axial motion, which means that it's oscillating up and down. Since it's a charged particle, it will induce a current into these electrodes. So if we now connect a resonance circuit here to these electrodes, we can measure this induced current, which is shown here in a simulation for a singly charged and a single silicon oxide molecule, which will induce a current which is large enough that we can amplify it with available commercially available amplifiers. And this is a technique which is well established in a mass spectrometry technique. They just perform a Fourier transformation and get this eigenmotion here out from which they can determine the mass, which is great. Okay, so moving on, we have performed extensive simulation studies and optimization studies and design studies such that we optimized the design and the electric field such that we have a maximum homogeneous electric field, which means that we reduced all the higher order coefficients in this electric quadrupole field such that the shifts on the axial motion are less than 10 to the minus 5 hertz compared to a frequency of 10 to the 5 hertz. So this is a perfectly harmonic potential, basically. And this is important because our particles need to experience a radio frequency field in order to mix these states of opposite parity. But how does that work if we don't apply radio frequency fields? Well, think about it in that way. If we have an oscillating particle in a static electric field, in the rest frame of the ion, it will experience a radio frequency field. And this is great because it's at the frequency of the eigenmotion of the particle, which we know and which we can measure very precisely. So this is great because we can control these fields very, very precisely. In addition, eventually we want to go for a cryogenic trap and a cryogenic resonance circuit because by that we can reduce the noise here, the thermal noise on our signal. So the goal is to put that down to 4 Kelvin, which will also improve our vacuum here. We also have performed extensive ion dynamic simulations using SimIon. We have performed ion transport simulations, ion injection simulations. We have performed simulations on the cooling through RF excitation and even the image charge detection. And we are convinced that panning traps can overcome all the, in quotation mark, downsides of the first generation experiment through these highly stable electric and magnetic fields, extremely long coherence times, which allow us to basically use lasers as long as we trap the particles, and the single ion sensitivity, which is important for the radioactive ion beam facilities. So here, a quick look on our setup. We have also a laser ablation ion source to create our molecules. We will ionize them and bring them down to their low vibrational ground state, and then inject them into our panning trap. The measurement scheme looks very similar to the one from the first experiment from David DeMille. So we will push these states of opposite parity together in the strong magnetic fields. We will prepare them in the negative parity state. They will experience this RF field, as I explained earlier, through oscillation in our DC potential, which gives us access to the parity violating part here. And then another difference to the setup before is that we will detect these particles not through fluorescence, but by breaking up only particles which ended up in the positive parity state. Because if we break up a molecule in our panning trap, since they are positively charged, the remaining atoms will still be trapped in our trap. So we can perform a quick mass measurement to determine whether we have a high mass of a molecule or a low mass of an atom in our trap. Okay, to give you a time scale on our experiments, we are moving an existing high precision magnet from TRIUMF. Jens Stilling is organizing this one which also includes a room temperature penning trap, which is already great because we can start systematic studies as soon as this trap and the magnet arrives at MIT in our lab. This is to be planned in summer 2021. We have performed full simulations of the existing trap and the magnet. We have performed full simulations and the design of this new cryogenic trap, which will be placed in the same magnet here. And once the trap is here, we will immediately start with systematic studies. We will in parallel also start production of this cryogenic trap, such that we can perform the first systematic studies of this cryogenic trap, hopefully next year or latest in 2023. And eventually we will then perform parity violating measurements on first stable isotopes. And for that, I would like to invite you for a discussion on suggesting us which molecules you would prefer us to measure. We have an idea about silicon oxide, which is a molecule for which there's extensive spectroscopic information already available. So there are laser cooling schemes already available. However, this particle is relatively light. So on this scale, which shows an additional amplification factor of these parity violating effects over the proton number, it would end up here. So it doesn't come with additional amplification. That's why we are also thinking about, for example, indium fluoride. However, there's no spectroscopic information available. Okay, with that, I'm at the end of my talk. I hope I could convince you that moving on to a penning trap, we can study these parity violating effects on a broad scale all across the nuclear chart eventually. And with that, I'm ready for questions.
Okay, thank you. Yes, please, any questions? Yes, before anybody maybe think about questions. Oh, there's, okay, good. Please, Andrei Yach.
Yeah, sure. Thanks. It's really interesting talk and nice concept. Penning traps are kind of amazing machines. I was just wondering if you could say more about considerations for state prep and you know, do you really need to fluoresce the molecules, or do you really need laser coolable molecules? I'm just kind of curious how much you guys have thought about the state prep aspects of the experiment, because molecular ions can be a little tricky.
Yeah, so using penning traps, especially cryogenic penning traps, allow us to couple the motion of the particles here directly to our resonator circuit. So if we cool that down to, let's say, 4 Kelvin, then the motion of the particle will couple here to that resonator circuit and directly cools down the motions of the particles. So we will eventually end up with 4 Kelvin cold particles if we go for this cryogenic trap without using any additional laser cooling or so. So this is already great, but of course, we want to perform our measurements eventually in their low vibrational ground state. So this is why accessing them by lasers would be beneficial. So this is why we are thinking about the silicon oxide, for example. If we would go for indium fluoride, for example, we would definitely perform spectroscopy before and see if we can laser cool them. Yeah. And then concerning the state preparation, we are aiming here for single particles. So for us, it's really crucial that we prepare these states here in this case, in this negative parity state, because if we don't, then we are starting with the wrong starting condition, basically. So yes, we need good spectroscopic information about the particle beforehand, which we can measure in our lab at MIT too.
Okay, just one comment. If it's a single particle experiment, you do have some, I mean, there are some potential options to do state prep, I guess, outside of the penning trap in your low vibrational ground state and then move into the penning trap. But
correct, yeah. So we will first start with a setup which is decoupled from our main beamline. But eventually we want to connect that to our beamline in the EMA lab, which offers us much more possibility to state prepare them, because we're planning also for some cryogenic RF traps. And there we have access also to maybe more possibilities for the state preparation. Yes.
Well, next questions from John Bear.
Just an obvious comment on picking a case. Jacek Dobachevsky and John Engel have told me earlier in the week that they're really interested in calculating antipole moments, so you should talk with them. I don't see John here, but I've never succeeded in getting a theorist to touch francium antipole moments and nuclear spin-dependent parity violations. So the light ones are great, but these are guys who might be able to do your other cases.
That's great. Thank you very much. Yeah, yeah, and this is why this workshop is also so great, because it brings together all this expertise, which is required also for measurements in the end. Thanks.
Yeah, sure, but you got to talk to him.
So next question from Moritz Reiter.
Hi, Jonas. Thanks for the nice talk. I was wondering, you were mentioning to do this now on stable molecules. Do you then plan to bring the magnet back to TRIUMPH to also sort of use radioactive molecules back over there?
So the plan is to do that in parallel. So once we have shown that we can do that on stable isotopes, we will apply for bigger funding and then hopefully build, let's say, the second generation of that kind of setup with a new magnet at a radioactive ion beam facility, and then in parallel also measure stable particles. Yeah.
Thank you.
Mm-hmm. And now Matt Grove.
This is a really interesting idea for an experiment. Since you're targeting single molecular ions and lots of different species, this seems like a natural combination with quantum logic spectroscopy. Would having an atomic logic ion in the penning trap ruin the systematics?
No, so as long as we are, let's say, in a few ion regime inside the penning trap, let's say below 5 ions or so, they will be far apart such that they don't interact with strong Coulomb interaction or so. If you go to higher ion numbers, then you can see in a mass spectrometry, for example, that these eigenmotions shift, and then you have to be careful about like direct interaction. But it's well established that you, for example, put a second particle inside the trap and then, for example, cool indirectly your particle which you want to measure by a particle, for example, calcium or so, which you can easily laser cool. So.
Wait, you said they're far apart, so they don't interact? I didn't understand.
Well, you can prepare them, for example, such that one particle is in the center and one particle is on a large magnetron radius, such that they don't interact, but you can also bring them close together if you want them to interact. So since you have full control over the motion, you can do what you want, basically.
Oh, I just would like to ask you, I have two questions. The last, could you go to your last slide?
Yes.
Could you explain a little bit more these two branches?
Yeah, I'm not an expert on that field, but I think that these are group 15 and group 13 molecules, which means that they have different chemical properties.
Kind of,
Yeah, exactly.
That's so okay. There's a bigger priority of the molecules. Yeah.
Yes.
Other things. Could you actually speculate if because your apparatus is very advanced. It's really very, very good one, as I understand. I work in these ionic molecules as theories, so I could say. But if we use radioactive molecules in your kind of environment, what do you think you may need to change something in there, or
No, so that's the beauty about this experiment. We can just take it and bring it to a radioactive ion beam facility. The only thing we are then restricted by is the half-life of the particles in principle. So we have to limit our laser interaction time, for example, to the half.
Yeah, that's true, right?
That is the only thing. And we are applying these penning traps already for 2 or 3 decades now in the mass spectrometry community at these radioactive ion beam facilities to measure something like nuclear binding energies.
Yeah.
This is my background also.
You can even use bigger molecules, right? Like
exactly. We are not restricted by anything, not by the mass, not by the number of particles. Yeah.
Yeah, that's beautiful.
These traps are really beautiful.
Yeah. You have a question from Luke Godwell, please.
Hi. I was wondering whether you could just say a little bit more about state detection. I guess some kind of laser fluorescence thing is one option, but I was wondering whether there were other.
Yeah, so what we can do, which I've been trying to explain here, but maybe that was not clear enough. So what we can do is we can use some 2 or 3 step process to break up these molecules. So it's really no need for any fluorescence detection. So we just break up the molecule in one state and leave the one in the other. If we have a single particle, that means either the molecule is broken up or the molecule is not broken up. And the molecule which breaks up remains still trapped as an atom. So it really has just a lower mass. And then we can perform these mass measurements through the image charge detection, which gives us very quickly an answer to, is the particle in the upper state or is the particle in the lower state? So it's not a spectroscopic detection, it's a spectrometry detection through the mass.
Okay, thank you. I missed that.
Okay, thank you. So we can go to next talk by Shin Inu. Do we have you here?
Yes. Yes.
Okay, very nice. So,
is my slide on?
Oh, not yet. No.
Not yet. Okay, let me make sure. Okay.
Don't see it yet. No.
Okay. Sorry.
No, it's okay. We have time. Don't worry.
Sorry about that.
Yeah.
Yeah, this way. This way, I guess. This and this.
Yeah.
Does this work?
Yes. Works.
Oh, you see it?
Yes, it's good.
Okay. So my name is Shin Inoue. Thank you very much. I would like to thank the organizers for giving me the chance to present our work in this wonderful workshop or conference. So the title of my talk is a measurement of the variation of electron to proton mass ratio using ultra-cold molecules produced from laser-cooled atoms. And I'm from Osaka City University, and my collaborators are Dr. Kobayashi in Hokkaido University and Mr. Ogino from University of Tokyo. Okay, so probably there's no real need to spend too much time on explaining the motivation behind looking into the variation of fundamental constants for this audience. But basically, people discuss about the possibility of the fundamental constants are changing over time, and that could be related to the big question about the dark matter or dark energy. So especially when we started the project, people were telling us that actually it could be related to the dark energy. For example, it could be related to something called quintessence, which is just like a classical scalar field that is spread over the whole space, which is really a low density, and that could be the source of the dark energy. And I think that recently people are paying more attention to the scalar field dark matter, which is also a classical field, and which is low mass and which is spread over the space, I think. And in both cases, people are speculating that since the density is so low, the mass is pretty small, but the frequency of the scalar field is related to the mass. So if the mass is really small, then the frequency should be also pretty small. And if that scalar field is coupling to the electromagnetic field or the ordinary mass, then you might be able to see the effect through the variation of fundamental constants over time. So the good candidate for looking into the possibility of seeing it is naturally like detecting the variation of the fine structure constant or electron to proton mass ratio or the G-2, etc., which is the fundamental constant which are measured with a pretty high accuracy. And during my talk, I'm going to use this notation of mu, which is indicating the ratio of the electron mass to the proton mass. Okay, so naturally atomic spectroscopy is a good candidate for looking into the high precision measurement. And people look into the optical lattice clock frequency and they see the stability of those frequencies with respect to the cesium frequency standards. And people got these kind of results in around 2014, showing that in the laboratory measurement, they could see the stability of the lattice clock frequency, which is converted into the stability of fine structure constant or the electron proton mass ratio. And the reason why electron proton mass ratio shows up is that the cesium frequency standards is basically depends on the magnetic moment of the nucleus of the cesium, which depends on the proton mass. So these are the pretty high sensitivity measurement on those stability, and they claim that they can see the stability in the 10 to the minus 16th level over 1 year. So at the same time, there are also other measurements using clever idea using the nice atom for measuring the stability of the fine structure constant, which is namely the dysprosium, which was done in Professor Badkor's group. And they use the dysprosium because dysprosium is a really nice atom because they have accidental degeneracy with 2 levels which belong to opposite parity. So if alpha changes, since these 2 levels are belonging to different parity, so if alpha changes, for example, if alpha increases, then this level, even level and odd level should move in the opposite way so that, and the shift should be proportional to this energy scale, which is on the order of the optical frequency. But since these 2 levels are quite degenerate, so for example, the frequency difference between these 2 are only like a few hundred megahertz. So there's a big win by measuring this radio frequency measurement. So almost complete degeneracy of these opposite parity excited states gives you a good sensitivity for measuring the stability of the fundamental constants over time. So with this measurement, actually, there is no need for using the optical frequency comb and so forth, but actually they can set up the experiment to measure this RF frequency, and they can get the pretty high precision for measuring this stability of alpha on the 10 to the minus 17th level over 1 year. Okay, so now actually what we have in our lab is the ultra cold molecules of bialkali atoms, which consist of potassium and rubidium. So we started to wonder maybe we can do we can contribute something to the stability measurement of electron proton mass ratio using this sample. So I'm going to report on this. So the reason why people discuss about molecular spectroscopy for measuring the electron proton mass ratio is that the molecular spectra is directly related to the inertial mass of the nucleus. So for example, if you imagine that the electron mass is constant, but proton mass is changing for some reason, then you can assume that the Born-Oppenheimer potential is constant, but so this potential is constant, but since the proton mass is changing, so the energy level spacing will be changed. So the vibrational spacing between these molecular spectra will be proportional to 1 over square root of the electron proton mass ratio. And also, of course, for the molecules, there is a rotational splitting, but that is inversely proportional to the inertial moment of inertia of the molecule. So it should be proportional to the 1 over mu. So looking in these values, you should be able to see the stability of the electron proton mass ratio directly from the molecular spectra. So people have seen us have done various measurements on these things. And for example, people measured the molecule spectra at a pretty distant place by observatory, using the measurement using the observatory. So we are not, I'm not the expert on this, but people done measurement on alcohol and other molecules spectra for in the galaxy and so forth. And they got the, I think there are more and more results accumulating, but basically the typical measurement was done over the 10 to the 10 year, and the accuracy they can get is on the order of like a 10 to the minus 6. So the if you assume the linear drift over time, then the sensitivity is on the order like 10 to the minus 16 over the 1 year. And I think this is a result from some review paper, but I think there is no definite answer yet. So with respect to the laboratory experiment, the thing we can refer to is the measurement done in 2008. So this is the direct measurement of the molecular spectroscopy to see the stability of electron proton mass ratio. And basically they observed the low vibrational transition of SF6, and they used the frequency comb to compare the cesium fountain clock, which was located in a different city. And by doing the precise measurement on this for about a year, and then they got the result, which is consistent with zero drift over on the precision on the order like 10 to the minus 14. So this was done with the room temperature SF6, but since we have ultra cold molecules, we thought maybe we can do something comparable or better than this. And actually, the important input was came from the paper by Professor Dave DeMille in 2008 that actually this bialkali molecules we have is quite suitable for doing this kind of spectroscopy. So the key is having that previously mentioned good degeneracy for levels which belong to different symmetries. So in the case of this bialkalies, in the ground state, there is a deep singlet state and the shallow triplet state. All of the bialkalies has these kinds of structure in the ground state. So if the electron proton mass ratio changes, then basically the level changes, the level change will be proportional to this step. So if proton mass changes, this singlet level moves, the singlet level changes a lot, and that change will be proportional to these steps. However, there is also adjacent triplet potential, and it also has a shallow bound state, but the bound state of this triplet level wouldn't move that much if the proton mass changes. So if you measure the difference frequency between these two bound states, then that frequency, which can be typically can be on the order of like a few hundred megahertz or so, could be quite sensitive with respect to the variation of electron proton mass ratio. So actually, since we have this potassium rubidium ultra cold molecules, we thought maybe we can use this for doing the measurement. So we actually looked into the real potential for the potassium 41 rubidium 57, what we have in our system. And so you can find in a couple of places, the bound states are almost overlapping each other. And of course, if you go too deep, then triplet and singlet level, even if those are overlapping, it is really hard to induce the transition between those two, so you can't really use it. And if you go really shallow, then of course, then those two levels actually start to behave in a similar way. So you have to find a good way in between. And we decided that 86 bound state of the singlet level and the 16th level of the triplet state are close enough. The frequency difference is on the order like a gigahertz. And so this is the good level to see the stability test. And actually, if you define the sensitivity as the frequency divided by the possible change of the mu, then you can define the figure of merit of using this level by dividing this sensitivity with the transition frequency. And that figure of merit is on the order like 10 to the 4th. So basically, this means that if you do the 10 to the 10 level of accuracy measurement, you can get the 10 to the 14th result and so forth. So we thought this is really a good molecular level we can use for doing this stability measurement. And of course, you can think about, okay, maybe you can try to find another factor of 2 or 3 by looking into other possibility and so forth. But basically, I think our feeling is that you can do the optical sensitivity. You can achieve the optical sensitivity by doing the microwave transition measurement is the key. So I think, basically this is good enough for the stability test. Okay, so now we know that we should make ultra-cold molecules here. And of course, you can consider various ways. And recently, of course, laser cooling molecules are really becoming a strong tool. But in those days, we have no idea how to do it. So our initial plan was rather a so-called indirect method, which means that we prepare ultra-cold atoms and then combine those two into ultra-cold molecules. That was the plan. So initially, everybody would think that the most straightforward way would be to produce GOBC of, say, potassium 41 and rubidium 87, and then do the magnetic field sweep to produce special molecules. And then after that, you can do the stirrup to bring that into the target state. And this is, of course, a really nice way to do the experiment, but actually, we didn't pursue this path just because there are a couple of reasons. of course, one of the reasons was actually we were plagued by some loss during the making dual BEC, but also we thought that this is actually too slow because we have to do the evaporation every time to make the BEC. So even though we can do the experiment repetition rate will be like every 100 seconds or so. So what we did instead was actually prepare your magneto-optical trap and then use this laser-cooled atoms, which is in terms of temperature 1,000 times hotter. But we can do the photoassociation and produce photo-associated molecules and then do the stirrup to bring that into the target state. So in this way, actually, the repetition rate of the experiment will be far higher because you can prepare the dual species mod in less than, or if like a 0.1 second. So the repetition rate of the experiment will be like 10 Hz, which is basically 1,000 times faster. So we decided to do this kind of experiment. So this is the energy diagram of what's happening during the experiment. You can prepare typically 10 to the 8 rubidium atoms and 10 to the 8 potassium atoms in dual species mod, and then do the photo association in the magneto-optical trap. And photo association means that you shine a single laser beam, and then the atom pairs will absorb that photon and then go to the excited state, and then do the spontaneous emission to go down to the ground state. So of course, this includes the spontaneous emission. You cannot really regulate which state these loosely bound molecules should form. So typically it's spread to like tens or hundreds of states. But then after that, you can select one of the levels and then do the stirrup, which means that you can transfer that molecules in the specific loosely bound state into the tightly bound state or any target state you want. So since you only deal with a single state in the loosely bound state, so you can produce 10 to the 2 or 10 to the 3 KLB molecules in the target state in the one experiment. So this is the typical number we cope with in the lab. So this is kind of the summary of the temperature and the number and the repetition rate of the experiment of our experiment. So the temperature of the atoms is on the order like 100 microkelvin because it is a laser-cooled atoms. And then the number of molecules produced in each time is on the order like 10 to the 2 to 10 to the 3. And the repetition rate of the experiment is like 10 Hz. And you can compare that with the Feshbach molecule plus stirrup experiment, which was typically done in Gila or other places. But you can compare those two and you can see basically the number is 10 to the 3 times smaller, but the rate of the experiment is also 10 to the 3 times faster. So if you multiply those two, then it's actually, you get a similar number. Okay, so in this experiment, we deal with a small number of molecules produced. So you cannot do the absorption imaging and so forth. So we use resonant enhanced multiphoton ionization to do the detection. And and this was incorporated from the experiments from the Yukon group in 2000 or so forth. So basically what they do was shine a pulse laser with a nanosecond pulse width, and then ionize the molecule by hitting some resonance. And then ionized molecule is detected with a channel tone or a channel tone. So we imitated this experiment. So this is the actual experimental setup of our machine. So we produce dual species magneto-optical trap and then apply CW laser to do the photo association. And then afterwards, we also apply stirrup, which consists of 2 laser beams, which is highly stabilized to a high finesse cavity. And then do the RF spectroscopy, which we need for the detection of the variation of electron proton mass ratio. And then finally detect the molecules in the after the RF transition with a resonance enhanced multiphoton ionization. And you can see this is a typical signal from the ionizing signal. And you can see that a clearly ionized molecule is distinguished from the atom by the time of flight of the ion. So the key is, of course, the stirrup, which is now really a standard technique in the ultra-cold molecular community. But of course, you have to spend a lot of time to find the good, proper excited state to connect the initial state and the target state. But once you do spend the whole time for doing the spectroscopy to find the right state, then the stirrup works pretty beautifully for the for ultra cold molecules. And this is a typical data, but you can just bring down and up the intensity of the 2 laser beam, and you can see that you can clearly toss the molecules back and forth between the 2 target states. And this is a typical experimental result. And you can see that you can recover about 50, in our case, we can recover about 50% of molecules after the round trip, which means that in the single trip, you can achieve the efficiency of about 70%. And so far, I didn't really talk about the drawback of using alkalis, but actually there is. And one of the drawback is that it has a lot of hyperfine states. So that is something we have to cope with. And this is, so we went through all the finding out all the details of the hyperfine transition, hyperfine state. And you can see that this is the actual hyperfine splitting of all the molecular levels associated with the almost overlapping states for measuring the electron proton mass ratio. And we decided to use this F equals 0, I mean, these 2 states. And we, of course, we use the 0-0 transition to measure the transition. So this is the typical, this is the actual experimental procedure. What we did, we prepare molecules with the photo association plus stirrup in the singlet state, and then apply the microwave field to transfer molecules from singlet state to triplet state. And then afterwards, actually, we pump out the molecules in this initial state by applying a CW laser, and then apply the resonance enhanced multiphoton ionization to detect molecules in this triplet state. And you can see this is a typical data, and which shows the ideal. You can see that it fits well with the sync function. And you might wonder what gives you this width of the frequency, which is about actually 50 Hz. But this comes from the fact that the molecule is not trapped. So the molecule is, the temperature is on the order like 130 microkelvin. So actually it diffuses during the measurement. And we basically apply the radio frequency wave of the 60 milliseconds, which is about the time that it expands about the size of the pulse laser. And this measurement time gives you the width of the frequency that you can measure with a single scan. So, and also important thing is to take care of the effects from the magnetic field. So we measure the frequency with a 0-0 transition, but then we also measure the transition frequency for a 0-1 transition, which is sensitive to the magnetic field to calibrate the magnetic field. And we do that with intermittently. So that we measure the magnetic field with this m=1 transition and then subtract the effect of the magnetic field to the second order Zeeman shift from this 0-0 transition. So this is a typical data you can get with the 6 hours of operation. And you can, after the subtraction of the second order Zeeman shift, you can get the final result, which is whose signal to noise ratio is about 500. And then also, you know, we are not really the expert of the precision measurement stuff, but we basically follow the steps of all the taking care of all the systematic effects as much as possible for our understanding. And for example, for the collisional shift, usually we get rid of the remaining atoms before doing the molecular spectroscopy by blasting atoms with resonant light. But actually, we intentionally kept this blasting beam off to see any effect of the shift of the frequency, and we didn't see any effect. So we can claim that the collisional shift is not affecting our experimental data.
Shin, your time is up, but we may probably give you.
Okay, sorry. Okay, yeah, sure. So, okay, we did take care of all the systematic errors, and okay, this is the final result. Basically, we saw the result basically shows that although our measurement is on the order like 10 to the 10, we get the 10 to the 4 win by that figure of merit. So the precision of the measurement is 10 to the 14th, which is about factor 5 better compared to the SF6 result. And our result is still consistent with 0 variation of the fundamental constant. So this is the conclusion. We measure the variation of electron to proton mass ratio using ultra-cold molecules produced from laser-cooled atoms, and that was consistent with 0. And also, some of the people might know that this actually experiment was done some time ago, and of course afterwards, people might be wondering what's going on. So actually, people who have done this experiment actually moved to a different university, and he's setting up the experiment in Hokkaido University, which is the northern part of Japan. And he's constructing a second generation experiment. And basically what he's trying to do is to trap the molecules. He wanted to trap the molecules. So he wanted to introduce the optical lattice. But in order to trap the molecules, you have to produce the molecules at the ultra-cold temperature. So you want to do cold to degeneracy, but you don't want to do the evaporation. So he's trying to implement the BEC via direct laser cooling, which was shown possible by MIT's Ladan group. So that's the current situation of the whole experiment. So sorry for going over time, but thank you very much.
Okay, it's very well. Yeah. Okay, so we have questions. John Burr, right?
Oh, just the obvious. Please show your systematic uncertainty slide again. You only had time to flash it. Thank you. Yeah, thanks.
Okay.
So next question by Michael Talbot.
Hello, yeah, thanks for the nice talk. I noticed that you've compared to the old SF6 measurement, but there are, of course, new measurements, clock comparison measurements from PTB that reach, I think, a few parts in 10 to the 17. So I wondered if you wanted to comment on that.
Yes. So, yeah, of course, 10 to the 16th measurement was really impressive, and I think it's quite important. We can say that this measurement assumes the relationship between the electron proton mass ratio to the magnetic moment, and our measurement is directly measuring the inertial mass of the nucleus. That's the thing. But I'm not the expert on this, so probably people in the audience can comment far better quality comments compared to me. Sorry.
So I use this chance that we have no questions yet, but I just want to ask you what your opinion. First of all, I would like to say the choice of potassium rubidium was excellent because I believe knowledge of potentials, very accurate potentials, is essential, right? And they're known very well. And then, of course, easily to calculate vibrational, rotational structures, whatever isotope you use. So therefore, there is a kind of interesting, maybe for us, that if you use, for example, another molecule like rubidium silver, there was discussion that silver really initiates some ionic coupling. What do you think? I would expect that X potential will be deeper, but A potential could be more shallow, as what we have some kind of experience. So doesn't matter, maybe to have maybe different lasers would be problem, or ionic coupling could also affect some your
purpose. But I mean, laser cooling silver we should require some work. So
okay, yes.
So in that regard, I would say increasing the number of atoms in this experiment might be easier in order to increase the sensitivity. In order to increase the precision.
Yeah, so then it would be interesting to understand how important is accuracy of potentials. It's not always potentials known very well. I mean, theory is pretty good right now, but still, it's not that exact as in experimental sense. So, because you're interested in sort of relative properties, it is okay. What do you feel if your potentials are not excellent, or is it important?
Yeah, I mean, if you don't really know the potential well, actually, for example, finding the right excited state for stirrup should be quite a lot of work. So in a couple of steps, you might need quite a lot of time to figure out good experimental condition. Yeah.
And then what about if you change isotope? I see you use 41 and there's a 39 for potassium. So would it be interesting, or it doesn't matter?
Yeah, I mean, that should be experimentally far easier, I think. Yeah, yes.
Yeah, and maybe other question about, you mentioned that your former postdoc, now trying to do experiment, create apparatus to. I understand it is important to have optical lattice, that you will be sure that molecules are controlled. But would it be okay to use tweezer, like number of tweezers? Or is it,
Sure.
because they kind of, as I understand, they allow you to have higher, little bit temperature, not so essential as a dipole trap. That could be a little bit higher temperatures.
Yeah. That should be definitely the possibility, I think. Yes.
Okay, so we have 1 minute for questions. If any question anymore, if not, then we go to next speaker, Evgeny Stadnik.
Thank you very much.
Mm-hmm. Okay.
So good morning, good afternoon, or good evening, wherever you may happen to be in the world. I'd first like to thank the organizers for the kind invitation to present this talk to you today. And what I'd like to cover in my talk is the possibility of using molecules, including radioactive molecules, in testing the fundamental symmetries of nature and looking for possible new physics beyond the standard model. I'm sorry, my slide doesn't seem to be changing.
Okay. That's okay, don't worry.
Maybe you can stop sharing and start it again.
Well, let's try that. I'm sorry about that. Okay, it's working now.
Mm-hmm.
Okay, so I'm terribly sorry about that. So over the past several decades, the prevailing classification in terms of how we systematically group the types of different EDM experiments in terms of their sensitivities to source of CP violation has basically told us that if we have diamagnetic systems which have no unpaired electrons, then these systems are believed to be mainly sensitive to hadronic source of CP violation. And these include experiments performed in atomic systems such as diamagnetic mercury and xenon. And they also include non-atomic systems like ultra-cold neutrons. It also turns out that if we have the complementary types of systems like paramagnetic systems which contain one or more unpaired electrons, then these types of systems are generally presumed to be mainly sensitive to leptonic source of CP violation, such as the electron EDM. And in this case, there have been a number of different experiments performed. So in older times, this was done using atomic systems like cesium and thallium. However, over the past decade or so, molecular EDM experiments have really started to take over the scene. And this was first done with ytterbium fluoride about a decade ago. And in recent years, thorium oxide and ionic hafnium fluoride have been providing the best limits on the electron EDM. Now, it turns out that if we consider not hadronic or purely leptonic sources, but rather semi-leptonic sources of CP violation, then the classification becomes a little bit more complicated. But again, there is some sort of simplifying classification depending on whether the underlying processes couple mainly to unpaired electron spins or to the unpaired nuclear spins. So paramagnetic systems would still generally be preferred if the semi-leptonic source of CP violation coupled to the electron spin. Whereas if the processes involve unpaired nuclear spins, then this would generally be preferred by diamagnetic systems. So the focus on this talk is using paramagnetic molecules. And we know that over the past decade or so, there's been tremendous progress with molecular EDM experiments in terms of their sensitivity to the electron EDM. In fact, over this relatively short period of time, there's been more than a factor of 100 improvement in the sensitivity to the electron EDM alone. So the main system in this case is thorium oxide. And although the focus of this workshop is on, generally speaking, short-lived radioactive isotopes, thorium oxide, one should also stress, is also a slightly radioactive molecule, but it's much more long-lived. Its half-life is of the order of the present age of the universe. The advantage of molecular EDM experiments comes from the fact that there is a very large effective electric field, which is seen by the unpaired electrons, which give the sensitivity to the electron EDM. So the typical effective electric field in molecules is of the order of 10 to 100 gigavolts per centimeter. And just to put this number into context, this is about 5 orders of magnitude larger than the largest electric fields that we can produce in the laboratory and apply in the experiment ourselves. Another interesting advantage, which is not the case in all molecules, but arises in the case of thorium oxide, is that in the experimental 3 delta 1 state, there is an enormously small magnetic moment, which is suppressed by a few orders of magnitude compared with the typical magnetic moments that we're familiar with in atomic and molecular systems. So this is an advantage from an experimental point of view because there is intrinsically less sensitivity to the effects of stray magnetic fields in this particular case. So we have better control over systematic effects in this case. But essentially the point that and the question that I'm trying to arrive at in this case is that seeing this very impressive sensitivity improvement for the electron EDM and the Planck source of CP violation, can we now also start to consider the possibility of using paramagnetic molecular systems to probe the complementary hadronic CP violation sources? Before we look at paramagnetic molecules specifically, I would just like to give a brief recapitulation of how hadronic CP violation manifests itself in diamagnetic atoms. The simplest example in this case would be this theta term, or this QCD vacuum angle, which is a term which is technically allowed in the context of the standard model. It involves the gluon field tensor G and its joule G tilde. And if we have this type of CP violating interaction, then we can induce a CP violating pi nucleon interaction vertex, which is the magenta vertex here. And we see that there is a mismatch in the CP character compared with the usual CP conserving vertex on the right here. So if we draw this loop diagram in here and we couple an external electromagnetic field to the pi line in this loop, then in this case we will generate an electric dipole moment of the nucleon. So in this particular case, this would be the neutron EDM. But if we redraw the diagram, this can also equally apply to the proton EDM as well. Now, nucleon EDMs, of course, operate for free nucleons as well as nucleons inside nuclei. But when we deal with nuclear systems which have at least 2 nucleons, then a second possibility starts to open itself up. And these are these CP violating intranuclear forces. In this case, at leading order, they're mediated by the exchange of a pion here. But the main characteristic feature is that there is again a mismatch in the CP natures of the pi nucleon interaction vertices at the top and bottom here. So CP violation again feeds in through the magenta circle here. And the external photon, if it couples to any of these nucleons, would then in principle allow us to generate a CP violating nuclear electromagnetic moment. And it turns out that at least for the case of the theta QCD term, the intranuclear forces, generally speaking, give a much larger contribution in nuclei compared with the nucleon EDMs on the left. The reason for this is that the process on the right arises at the tree level, so there are no loops here, as opposed to the nucleon EDM on the left, which has this loop structure here. And so by avoiding this loop suppression factor, the tree level processes, generally speaking, will give us the much larger contribution. Now, how do these hadronic CP violating effects actually get communicated from inside the nucleus to the external observer? This is something which is quite interesting because it's complicated by a result known as Schiff's theorem, which basically tells us that if we have a neutral atom, which is made up only of point-like non-relativistic charged particles, and assuming that these particles only interact electrostatically with one another, so no magnetic interactions, then in this case, the constituent electric dipole moments of these point-like particles will be screened from the effects of an external electric field. So this is a very wordy statement, but it has a very simple classical explanation from the point of view of a point-like nucleus. And that is, if we take this neutral atom and place it in external electric field, the atom as a whole will not accelerate. To see why this arises, we can take the atom here and apply the electric field. And what we see in this case is that the positions of the electrons would adjust in such a way as to ensure that the total electric field at the center of the atom will remain zero. So this ensures that the atom does not accelerate, but it also implies that there's no electric field vector with which the nucleus can potentially interact with in this case. Schiff's theorem is, of course, a very idealized theorem, and in realistic systems, it's broken by a number of different types of effects. In the case of heavy atoms, from the point of view of the nuclear EDM, the relevant and dominant source of lifting of the Schiff's theorem is due to the finite size of the nucleus. And so we see that when we allow for the nucleus to have a finite size, the electric field vector can now be non-zero. The total electric field can be non-zero at the points away from the very center of the nucleus in this case. So now this nucleus can interact with an external electric field, although the interaction is going to be somewhat suppressed compared to the interaction of an hypothetical interaction of electric dipole moment of the nucleus in a bare atom. And we parameterize the observable effects by something known as the nuclear shift moment. And without going into technical details, essentially the nuclear shift moment can be interpreted or thought of as a screen nuclear electric dipole moment. So this brings us now to the question of how we can probe the effects of hadronic CP violation in paramagnetic molecules. Well, the story here is in fact more complicated because these hadronic CP violating effects only start to rise at the 2-loop level or higher, and they arise via 2-photon exchange here. So there are a number of different types of diagrams which contribute in this case. At the formally leading order in the pion mass, which corresponds to these CP odd nucleon polarizabilities, we see that there's essentially a correlation between the electric and magnetic fields of these two internal photon lines over here. And the source of CP violation enters through this magenta vertex down the bottom here. And this can be communicated all the way through to the interaction with the electron via the exchange of either a pi meson or an eta meson. And we see that the bridge here is this big gray vertex over here, which is a one-loop vertex arising in the standard model here. Then we have the formally next to leading order contribution in the pion mass. And here, when we expand the diagram, we see a relatively intertwined contribution. But again, all this corresponds to is a CP odd nucleon polarizabilities, where there's again a correlation between electric and magnetic types of the internal photons. And now the basic idea is that one of the photons interacts with the electric moment of this charged pion line inside the loop over here. And the second photon interacts with the magnetic dipole moment of this internal nucleon state over here. Finally, there are also types of processes which don't fall under this simple categorization or parameterization in terms of the pion mass. In particular, the most common example would be this 2-photon exchange process via this box type diagram. And in this case, again, one of the photons interacts with the magnetic dipole moment of the nucleon state, of the nucleon, and the second photon interacts with the electric dipole moment of the nucleon. And in most types of models of CP violation, the electric dipole moment of the nucleon would arise at the 1-loop level or higher. So this process is at least 2 loops or higher in this case. And in this type of process, at least in the Fermi gas model, we see that the relevant energy scale or momentum scale which enters is not the pion mass scale, but rather it's the Fermi momentum scale, which is comparable to but slightly larger than the pion mass here. And on top of this, there's this extra enhancement factor, which is logarithmic in the number of nucleons inside the nucleus. And this is associated with the nucleon states which lie close to the Fermi surface. And we'll see a little bit more of explanation about this on the next couple of slides. So the basic observation with all these types of two-photon exchange processes is that one of the photons in all of these processes interacts magnetically with the nucleus. So if we recall the conditions of the Schiff theorem, which only applied to electrostatic interactions, then we see that the conditions of the Schiff theorem are not met, and therefore there's not going to be any Schiff screening in this case. So we avoid Schiff suppression factors, which are typically of the order of 1,000 in heavy atomic systems. Another very interesting feature of these types of processes is that they correspond to the CP-odd nuclear polarizability, which is of the scalar type rather than a vector or a tensor polarizability. And the scalar nature of the polarizability implies that all of the nucleons inside the nucleus can coherently contribute at once and enhance the overall effect by the total number of nucleons inside the nucleus. And because this is a scalar polarizability, the other very interesting advantage is that this mechanism operates even in the absence of nuclear spin. So this is very different from the usual nuclear shift moment, which requires us to have a nuclear spin of at least 1/2. And because this applies to spinless nuclei as well as nuclei with spin, we can also apply this to the experimentally interesting and very currently relevant species of thorium oxide and hafnium fluoride, which are currently giving the two best limits on the electron EDM at the moment. So let's look at some specific hadronic CP violating sources in this case. First of all, we can look at the formally leading order contribution, which we drew earlier, and consider simply the exchange of a pi-naught meson between the nucleons and electrons. So what we mean by isoscalar coupling here is this type of interaction constant. We just have the neutral pion, and it couples to the nucleons in such a way that ensures that the nucleon state or flavor doesn't change at the vertex here. So if we have a neutron, it remains a neutron afterwards. So the nice feature of looking for this type of coupling specifically is that if we have a molecule with a spinless nucleus, such as in thorium oxide or hafnium fluoride, the effect is actually dominated by a bulk property of the nucleus, which is going to grow with the total number of nucleons in a regular manner. And because these nuclei in this case are spinless, there is no contribution from the usual nuclear shift moment mechanism, which would require us to have a non-zero nuclear spin. So the advantage of looking for this particular coupling with paramagnetic molecules is it actually gives us access to very clean and robust bounds because there is significantly less sensitivity to the details of the underlying nuclear structure and dynamics. For comparison, we understand that in interpretations of nuclear shift moment type experiments, there is generally speaking strong sensitivity to the assumptions about the underlying details of nuclear structure and dynamics. In fact, in the case of the Mercury shift moment, different nuclear models actually give different signs for the underlying sensitivity coefficient. So the robust interpretation of the Mercury EDM experiment is somewhat challenging, and some would argue potentially even unsatisfactory. The next type of hadronic source of CP violation which we can consider are nucleon electric dipole moments. So in this case, the relevant process is the box type diagram, which we drew a couple of slides earlier. And in this case, the key feature of this type of process is the possibility of internal nuclear excitations via this internal nucleon leg over here. There are two broad types of excitations that we can have. First of all, we can coherently excite all of the nucleons inside the nucleus to go above the Fermi level in this case. So if we look at this in the context of the Fermi gas model, we see that because we're exciting the nucleons by a relatively large energy of at least the Fermi energy in this case, the relevant energy or momentum scale which enters into the denominator is going to be given by this relatively large Fermi momentum scale, so about 250 mega electron volts. There is also this logarithmic enhancement factor in the total number of nucleons, which is associated with the nucleons which lie close to the Fermi surface in this case. In addition to this continuum contribution, there are also contributions from the discrete transitions between spin-orbit doublets. So here we see that we only have to excite the nucleons by a relatively small energy in this case, which is of course much less than bringing the nucleons out into the continuum. So now instead of the Fermi momentum scale, we can have a much smaller nuclear energy separation gap in this case. However, because the transitions are taking place between relatively small numbers of nucleons in this case, of the order of 10 or so, the excitation is not fully coherent, which means that while we do benefit from the smaller denominator, we do get suppressed by the smaller number of nucleons participating in the process. What is quite interesting, though, is that if we take a relatively heavy nucleus, which has about 200 nucleons, and consider the typical energy level separations between the spin-orbit doublets, which are of the order of several mega electron volts, then it turns out that these two contributions are not only comparable in size, but at least for the nuclei considered in these two papers over here, they also happen to be of the same sign, which is very nice. And finally, we can come to the perhaps the most interesting and certainly the most complicated contribution for paramagnetic molecules, which is the QCD vacuum angle, or the theta parameter here. So in this case, we actually have to consider all three types of processes which we introduced earlier. And first of all, we see that this formally leading order process in the pi mass receives contributions from not only the pi naught meson, but also from the eta meson. And these contributions enter with the opposite sign here. And this is particularly interesting because if we consider heavy nuclei, which are of interest in experimental searches, the two contributions nearly cancel here and give a much smaller contribution than we would naively expect from the leading order process. On the other hand, for the formally next to leading order process and the box type diagram on the right here, there is no such cancellation. In particular, if we look at the next to leading order process, the pions in the loop here are charged. So they appear as part of an iso triplet together with the pi naught, whereas the eta meson is an iso singlet. So there's no corresponding eta plus or eta minus to enter into the loop here. So therefore, there's no cancellation similar to the formally leading order process in this case. And additionally, the proton and neutron contributions in the nucleus all add with the same sign. And this is true for the next to leading order process and the box type diagram on the right. And even more importantly, the two contributions here are also of the same sign. So if we look at a particular example for a nucleus which has about 80 protons and 200 nucleons, we can parameterize the contribution of all three of these types of terms by the effective effects of this contact CP violating interaction between nucleons and electrons. And we see that the formally leading order contribution gives the smallest contribution in this case. This is because of this accidental cancellation. And then we have the somewhat larger contribution from the second process. And the box diagram, even without discrete excitations, already gives the dominant contribution in this case, which would be about double this if we include the discrete contributions. In the future, this is something which I think would be potentially of interest to the nuclear physics community. It would be interesting to also include the contributions of the eta prime meson and other formally next to leading order contributions. In addition to this, the middle process here could also benefit from a more detailed treatment of the nuclear dynamics, because the nucleon propagator over here is technically not a free propagator, but it's of course subject to the effects of the nuclear medium. And finally, in the case of the box diagram on the right, there are also the effects of nuclear structure which can be considered. So this has been done in the context of a very simple nuclear model, but it would also be interesting to have more detailed nuclear calculations for this. So these are the bounds which we obtain, at least for these hadronic CP violation parameters. So we have the isoscalar pi-nucleon interaction. We have the linear combination of the quark-chromo electric dipole moments. And then we also have the proton EDM and the theta QCD term over here. So the thorium oxide bounds which we derived are shown in the first row over here. And what we see is that the current bounds that we can get from molecules are about a factor of 10 to 100 times weaker than the bounds from mercury and neutron. But at the same time, the thorium oxide bounds are actually 10 to 100 times stronger than the current best limits from the xenon EDM experiment. There is one other caveat in this table, which is that for the case of the isoscalar coupling and the quark-chroma EDMs, in this case, there is significant uncertainty with the nuclear shift moment interpretation. In principle, the actual signs of the sensitivity coefficients, the sign of the sensitivity coefficient is uncertain, and therefore the sensitivity coefficient could in principle be consistent with 0, which would nullify the bounds. If we accept this criticism, then in this case, the thorium oxide bounds are about a factor of 4 weaker than the best, next best bounds from the neutron EDM experiment in the second row. So in the last several minutes, I'd now like to give a brief overview of how we can use molecular systems to look for possible dark bosons. And the simplest way in which we can look for dark bosons by their parity and time reversal violating forces is if we have the exchange of a dark boson between two fermions, but have one of the fermions interact via a pseudoscalar type vertex and have the second fermion interact via a scalar type vertex. So in the non-relativistic limit, this would give rise to this characteristic potential here. And the characteristic feature of the potential is that it involves the correlation of the first fermion spin, which ideally should be unpaired. And it's also going to be a scalar product with the radial vector from the first fermion to the second. So because this is a parity and time reversal violating correlation, the exchange of this dark boson between the constituents of an atom will give rise to atomic and molecular EDMs due to the parity and time reversal violating forces within the atom. So previously, these types of dark boson exchanges have been considered in the context of only relatively heavy dark bosons, where the range of the interaction is very short because of this exponential factor here. What we actually did for the first time in these two papers here is consider the opposite case of having a dark boson, which is very low mass. And in this case, essentially the parity and time reversal violating forces would act on a long range as far as the scale of the atomic and molecular system is concerned. And this is a somewhat technical detail, but nevertheless quite interesting. And that is that the non-vanishing contribution in this case arises from this somewhat unconventional Thomas Fermi length scale, which is a semi-classical length scale that consists of a combination of the atomic Bohr radius and a fractional power of the nuclear charge. So the limits that we get when we do this are shown by the region in red. These are with the best molecular EDM experiments, namely thorium oxide and ionic hafnium fluoride. And basically the main take-home message from this graph is that molecular EDM experiments are capable of probing larger dark boson masses than the more conventional experiments in gray, like the torsion pendulum experiments and co-magnetometers, because the experiments in gray are probing interactions in macroscopic length scale. And in that case, because it's a macroscopic length scale, the dark boson mass has to be much smaller in that case in order for the dark boson to reach one test body to another. And in the last couple of slides, I would also like to discuss the possibility that these dark bosons may also in principle saturate the observed dark matter. So we understand that there's a number of independent astrophysical observations which collectively tell us that there is about 5 times more dark matter in the universe than the ordinary visible matter around us. We understand that the majority of the dark matter is confined to the galaxies, where it forms these spheroidal dark matter halos. And from the point of view of detection experiments in the laboratory, in the vicinity of the solar system, we understand that the average energy density of the dark matter is very small compared with the matter-based densities in terrestrial environments. And also we understand that dark matter should be non-relativistic, at least in the galactic halo. So one of the interesting possibilities for dark matter is that it may consist of very low mass dark bosons, which comprise a coherently oscillating classical field phi. So the angular frequency of the oscillation in this case will be governed by the mass energy of these low mass dark bosons. And we'll also have this angular frequency of oscillation phi naught, which is fixed by not only the mass of the dark matter particle, but also by the energy density in the local environment. So this is just the dependence that we would expect for the usual harmonic oscillator like the one on the left over here. So one of the interesting possibilities in terms of looking for these oscillating dark matter fields is if they interact with the gluon field tensor and its dual in much the same way as we would have for the theta term in the standard model. In fact, the substitution is very simple. We have a static parameter being exchanged for a combination of terms, which is oscillating in time now. And therefore, we can essentially carry over most of the results which we mentioned earlier in the talk, at least in the case of the limit of adiabatic oscillations here. So basically, we just have an oscillating electric dipole moment of the system, and the angular frequency of oscillation is governed by the mass of the dark matter particle. So these are the limits which we have on the interaction of the axial dark matter field with the gluons. And to date, there are two especially relevant sets of oscillating EDM constraints which are available. The first one was obtained by the NDM collaboration. This was using ultra-cold neutrons with mercury as a reference. And so in this case, the limits on this dark matter interaction parameter are shown in dark blue. And then more recently, we've also had limits from a reanalysis of the hafnium fluoride molecular EDM data, and these give the limits shown in light blue here. So basically,
time is up.
Okay, so I'll finish now. So basically, for those dark matter particle masses, the NEDM bounds here give a very sizable improvement over the astrophysical bounds in red and green. And thank you very much for your attention.
Thank you. So, any questions? Oh, no questions, but maybe just maybe talk about your summary.
Oh, okay. In that case, if nobody has any questions, well,
yeah.
Actually, so I described some of the possibilities in which we can use molecules, as well as also radioactive molecules, though it's not specific to the radioactivity of the molecule, in terms of how we can test the fundamental symmetries and look for new physics. So as the main topic, I described a very recent result of ours, where we essentially pointed out that paramagnetic molecules can be used as quite sensitive probes of hadronic source of CP violation via two-photon exchange processes. So this is complementary to leptonic sources of CP violation like the electron EDM. And the very nice feature of the two-photon exchange processes is that they operate regardless of the type of nuclear spin that we have. In other words, we can look for these hadronic sources of CP violation in the case of spinless nuclei. So we open up experimental possibilities, and we can already apply this to the experimentally very relevant and important molecules like thorium oxide and ionic hafnium fluoride. I briefly discussed how the exchange of low mass dark bosons and side molecules can give rise to so-called long-range parity and time reversal violating forces, and this would generate permanent EDMs in molecules as well as atoms. If these dark bosons comprise at least some fraction of the observed dark matter, then they can in principle also induce oscillating time EDMs, which can be solved with, in some cases, very similar techniques to permanent EDMs. And in terms of future work, I briefly mentioned in the case of two-photon exchange processes that we would like to ask the nuclear physics community to consider the possibility of investigating the nuclear structure effects and dynamic effects in more detail, the inclusion of the nuclear medium in the calculations, and also the high order contributions from the eta prime meson and the formally next to leading order contribution. And the final 2 points I didn't mention in the talk specifically, but I think this would also be very useful, definitely in the context of radioactive molecules. There are various exotic nucleon spin-dependent phenomena which could benefit from improved calculations of the proton and neutron spin contributions in heavy nuclei, which is particularly difficult in the types of deformed nuclei, which are often radioactive. And in addition to this, another interesting area of improvement, which we ideally could very much use, is improved calculations of the nuclear shift moments of heavy nuclei in particular, the refinement of different nuclear models to give us better agreement, for example, in case of the Mercury shift moment, but this is also very relevant, for example, to radium-225.
Okay, so we have question from Shane Wu, please.
Yeah, thanks for the very nice talk. I have a question related to the last part of, you briefly mentioned the time oscillating EDM. I'm just wondering what are the most interesting frequency range that you would think it's most relevant for looking for this time oscillating EDM?
So interesting is anywhere in principle from about 10 to minus 21 or 10 to minus 22 electron volts and up. The basic reason for that is that there's a relatively hard lower cutoff mass, because if the dark boson mass becomes too small, the de Broglie wavelength of the field grows very large. And so eventually there will be contradictions with the observed structures that we see, for example, in galaxies and around galaxies. So the best motivated cases should be at least about 10 to minus 22 to 10 to minus 21 electron volts. And above it, there's essentially no limit, with the only exception being that we need to have a sufficiently large number density of these bosons to have a classical field in order to see this wave-like oscillation of the field. And that upper cutoff arises at around 1 electron volt, where the frequency is about 100 terahertz. So that's the infrared region of the electromagnetic spectrum. So frequencies from 100 terahertz down to a period of oscillation, which is about a month to a year, would be the most interesting frequencies in this case.
Okay, thank you so much. And now we end our session, and we have a break for 15 minutes.
Excuse me, Svetlana, are there breakout rooms as well?
Yeah.
Yes. So yeah, we will ask the speakers to go to different breakout rooms.
Oh, okay.
And we will be joining. So now it should be ready.
And we join according to the talk number.
Right. Yeah.
Thank you.
At least I was told. Okay, good.
Hello, Svetlana. I just want to make
Yes.
sure you can see my slide.
Yes, perfect.
Okay, awesome.
Yeah, very good. So we will start in 1 minute.
Yes, and I'll probably finish ahead of time, but do feel free to remind me if I'm going close to it.
Yeah,
I have a very simple talk, so I probably won't go too long.
but maybe speak more slow. It will help.
Very slowly.
Okay, we're now starting our last session, kind of before discussions. So first talk by Amar Woodford, please.
Thank you very much. It's been an intense and tremendously interesting week, and I want to thank everyone for putting this together. It's also not often that you get to be on the International Advisory Committee for a workshop and a speaker at it, so thank you for the double privilege. I wanted to speak about something very specific and simple because it has been quite a long week, and so I want to tell you a bit about this new technique that we came up with for trying to do EDM measurements using clock transitions in hyperfine states of molecules. So the work that I'll describe is spelled out in this paper, and this was carried out with Mohit Verma, who is now at the University of Chicago, and Andrew J.H., who you heard from on Monday. If there's been one message from this entire workshop, I think it's been that there are lots and lots of choices here, right? We have an entire periodic table to play with, not even counting all the different isotopes that are ready to pour out of all of the rare isotope beam facilities. And if you now start pairing up these atoms into molecules and bigger molecules and even more complicated animals, the world's your oyster. There are lots and lots and lots of choices. But with lots of choices comes a bit of responsibility. And so let's make a wish list and try to say what we would like from this beautiful, perfect molecule that's going to solve all of our problems. So I think everyone will agree that the first thing you'd like in this business is for the molecule to be easily polarizable. All right, let's give ourselves that. We like that because we can work with small electric fields. Great. We'd like something with a heavy atom in there because we all know that relativity and heavy atoms give us extra amplification. The theme of this conference, if anything, has been that if you get a nucleus that's sufficiently non-spherical, you also win big. You get great big shift moments and other sort of goodies. But of course, you'd like all of this to not come with a price. And so let's also ask that we'd like something with a small magnetic moment. I hope you can see what I'm building up to. So if you add on more and more things to the wish list, because of course it would be awful if we had all these things, but the molecule was impossible to produce. And so let's also ask that it's easy to produce at our favorite facilities and our favorite labs. But if you'll allow me to think a bit like an engineer for a second, if you pile on a lot of orthogonal constraints on some very large parameter space, it doesn't take too long before you start to end up with something that's boxed in, and perhaps you'll even find that there really aren't very many options left the more and more greedy we get with our wish list. But let's keep going regardless. So of course, we'd like it to be laser coolable and get to ultra cold temperatures with, let's say, about 20 lasers. But let me maybe revise this up because there are lots of courageous people at this workshop. So let's say, let's call it 100 lasers. All right. On top of that, that's not enough though, because we would like it to get even colder. So good, let's ask for good collision properties. Or if you're of the persuasion where you say, well, you'd like to assemble molecules from laser coolable atoms, great. You'd like it to be assembled into its quantum ground state without too much trouble. And let's not forget that we all love co-magnetometer states, because even with small magnetic moments, it's a real pain to keep track of magnetic fields. All right, so I think that's a pretty good wish list. And perhaps most of you will agree with me. There's a word in German for this kind of thing. Of course, there's always a word in German for all sorts of things. That's the word. And my German's not perfect, but it loosely translates to mythical molecule that will satisfy your darkest desires and get you your Nobel Prize. Okay, so the point I was trying to make is that asking for too many of these things starts to get us into the sort of territory where we'd like lots of crazy features from our molecule, which may be sort of losing the plot a little bit. And so what I want to do is ask if there are any constraints that we can relax in this list. And even if we do relax a few constraints, that's still a bonus, and that might still mean that there are more choices open to us, less exotic molecules or less exotic isotopes that we can work with. And so in general, freeing up some of the design constraints on our molecule might not be a bad idea. So the thing I'll focus on is this magnetic sensitivity of the molecules, the things that we don't really like. And so to get to the bottom of it, let me just sort of start with a review of how we think about EDM measurements. And again, I realize this is a diverse audience of people who are not really experts in AMO. So I've tried to keep the discussion at a slightly basic level. And so I hope some of my more experienced and expert EDM colleagues will give me some slack. All right, so the simple picture is that we look for EDMs by looking for extra torques. We look for extra torques beyond the torque we would expect from just putting our spins in magnetic fields. And that extra torque is the signature that leads to extra spin precession we like to measure. You can think about this exact same thing in the language of Hamiltonians and energy shifts. The idea is that you have a spin interacting with a magnetic field, which gives you some magnetic component of the energy shift. And then the interaction of the EDM with the electric field gives you a little bit of extra stuff. And both of these things add together and give you a total energy shift. And the point is that by measuring this energy shift and by checking whether the EDM effect adds or subtracts from the magnetic field, that's how we sort of pick out the measurable effect of an EDM. The standard approach to measuring anything of the sort goes back to Norman Ramsey, as with most things. And this approach has been phenomenally successful with a few notable exceptions like solid state experiments. This has been the basic idea that almost every EDM experiment has used, whether it's neutron EDM experiments or with atoms or with molecules. And so here's my quick sort of graphical version of what the Ramsey technique is for anyone who hasn't seen it before. The basic idea is that you're trying to measure this energy difference. Let's dispense with all of these symbols and just write it simply as a magnetic part of the energy. And then some parity and time reversal violating part of the energy, which we'll call as coming from the EDM. But of course, you can be more specific and think about scalar, pseudoscalar, etc., whatever you like. And so this thing on the right is a block sphere. It's just a graphical representation of the quantum states of the system. There's a spin down state at the bottom on the South Pole, a spin up state on the North Pole. So step one is you do something to prepare yourself in one of these states. You start in the South Pole, let's say. In the next step, you make it from the South Pole up to a point on the equator. And this is the state preparation step. After which you let your system evolve under the action of this electric and magnetic field combination. Due to the magnetic field, you pick up a little bit of phase in some time tau. And then due to the EDM effect, you pick up a little bit of extra phase in that same time tau. And so this phase angle contains all of the information about the goodies that you'd like to measure. But it's hard to measure phases directly in the superposition of two states. So you map this phase onto a population difference, which you can now measure using your favorite technique to measure population differences. Okay, so that's the basic idea, that this phase due to the magnetic and the EDM effects got mapped onto population differences. You can extend this idea to things beyond just a single spin. So for example, if you're in the ground hyperfine manifold of your favorite molecule, let's say something with an F equals 0 and F equals 1 set of states, you can do the exact same analysis, except now you can think about these two states, the states with both the electron spin and nuclear spin pointing together, let's say, and the state where both of them point down. Those two states can now be your two-level basis states, and exactly the same logic follows. Instead of thinking of this as just a spin down state, you make one of your hyperfine sublevels the thing at the South Pole, the other hyperfine sublevel is the thing at the North Pole, and the exact same logic follows, that you're measuring the combination of a phase due to the magnetic field and a phase due to this EDM effect. Let's dig a bit into hyperfine states to sort of understand a bit more. So if you pick a simple molecule, a simple doublet sigma molecule, and since this is a radioactive molecules workshop, it sort of behooves me to pick something reasonably radioactive. So let's say we're working with the spinless isotope of radium stuck on to a fluorine-19. So this has got one valence electron spin. And then this comes from the fluorine nucleus. All right, and of course, this molecule itself is going to have some electronic structure. It's going to have some vibrational structure, and the whole thing, of course, can rotate about an axis perpendicular to the molecular axis. And so all of that we will consider, but let's assume that we've frozen out the electronic motion and we're sitting in the ground electronic state. Let's also assume that you're working at low enough temperatures that you don't have to worry about the vibrational degree of freedom. And so then what you're left with is the rotational Hamiltonian. This is the thing that'll contain terms that look like B, J, J plus 1. And then it'll have things like the spin rotation interaction, let's say, if you want. This hyperfine term includes familiar things like the spin dot I, but you can also have tensor interactions that look like, for example, things of that sort. These next three terms are going to be the star players in the rest of the story. So let's maybe write these out carefully. So the electric interaction of this molecule, this polar molecule, is a very simple term. It looks like the molecular frame dipole moment times the unit vector pointing along the axis of the molecule, dotted with the lab electric field. This magnetic term, again, looks quite simple. All it is the G factors for the spin and the nuclear spin dotted with the magnetic field. And then finally, this HEDM, which is the thing we care about, if you think about what this effective operator looks like, acting only on these rotational and spin degrees of freedom, this thing can almost always be parameterized as some constant, which our AMO theorist friends can calculate for us. And then the spin vector, in this case, let's assume that it's only the electron that contributes, dotted with this intermolecular axis n hat. Okay, so these three terms are the main parts of the story. There's a coupling between the spin and the axis. That's zero unless there's some kind of parity and time reversal violation. There's a coupling between this molecular axis and the lab electric field. That's the standard handle to point the molecule in different directions. And then there's a coupling between the spin and the magnetic field to no one's surprise. If we now think about applying an electric field to this molecule, well, the molecule polarizes in the field, and you get this sort of dependence of the Z projection of this internuclear axis of the molecule as a function of the electric field in some convenient dimensionless units. Okay, and so in a static electric field, well, it doesn't have to be static, but in an electric field and a magnetic field, which let's say we've pointed along the Z-axis, the Hamiltonian that has to do with the hyperfine states of your molecule looks like the usual hyperfine Hamiltonian that you would get in the absence of any perturbations. This magnetic term that we've just met, except with only the Z components. And this parity and time reversal violating term, except instead of S dot n, what you really have is this quantity, which is just the projection of n onto the Z-axis. And this thing I'll call zeta for convenience, and we'll see this in the next few minutes. But now if you go and stare at what the hyperfine states actually look like, again, this is a simple case with only 4 hyperfine states. There's an F equals 0 state where the nuclear and electronic spins are anti-parallel, and then you have the triplet states in the F equals 1 manifold. And focusing our attention on only these two states, we can write down a Hamiltonian in the subspace spanned by these two states, and it's just some simple 2 by 2 matrix. In fact, it's a really simple 2 by 2 matrix. All it's got along the diagonals are the combination of this Zeeman interaction term, which contributes to omega b, and this thing that contributes to omega pt. And our task is to measure omega pt and check whether this quantity is 0 or not in the experiments. Okay, and so that's all there is to it. It's a really simple Hamiltonian. And that's why, for example, you can think of this as all it's doing is adding a phase in this block sphere that has the spin down state, the double spin down state in the south pole, and the double spin up state in the north pole. So there's a magnetic effect that adds to an EDM effect. So this is the standard technique. This is Ramsey's technique, or the modification of it, which we'll call the spin interferometer. The real problem with this is something that has been talked about many times. I borrowed this slide from Jaideep. Thank you very much, Jaideep, where he, on day 1, alerted you to this fact that if you see any kind of magnetic field that's not controlled, well, that adds to these terms in the diagonals. Okay, and the bad stuff basically adds along with the EDM stuff that you'd like to measure. And that's the real problem, is how do you separate the EM from this bad stuff, from the magnetic stuff? Okay, so that's the real problem with this basic technique. And that's the thing which we all try to fight by trying to find good molecules, by trying to find states which have comagnetometers and all that sort of fun stuff. What I'd like to do now in the next few minutes is convince you that these two states that we don't really bother with usually might actually be quite interesting in their own right. So these two states are the Bell states, if you like, or the even and odd combinations of up, down, and down, up. The Hamiltonian is exactly the same. It's the same hyperfine states, but restricted to this 2-state subspace. Now the Hamiltonian looks a little more interesting. So now all of the Zeeman stuff, which used to be in the diagonal, remember, has moved over to the off diagonal. That's the magnetic field interaction. And so this leads to what I'll call big omega b. This stuff leads to big omega pt, which is the parity and time reversal violating effect. And then there is a unperturbed energy difference between these two states due to the hyperfine interaction, which we'll call little omega naught.
Okay, so this matrix looks a little different. It has a little different structure, but this is a very standard matrix for anyone who's done two-level atom spectroscopy. All you're doing is you need to drive this transition at the frequency omega naught, little omega naught. And so on the Bloch sphere, it looks even simpler. And so the approach is you start off in one of the states. Let's say you start off in the f equals 0 state. And then all you do is you drive the system with oscillating magnetic fields and oscillating electric fields, through the combination of which you pick up an angle, except this angle is no longer a longitude angle, this is a latitude angle. But that's it, that's all there is to it. You start off in one of the eigenstates. It's really simple, you don't have to prepare any superpositions. You drive it, and then you measure what the population is at the end of it. This is so simple that Rabi invented it before Ramsey did. And so this is nothing but Rabi spectroscopy. In an extremely exaggerated version, let's look at what the excited state population looks like. In the excited state, I just mean the state up there. The excited state population is a function of the magnetic field times the magnetic field amplitude times the time for which you light up this molecule with oscillating magnetic fields, has the usual Rabi oscillation curve. But the neat thing now is that if you phase the electric fields slightly differently from the magnetic fields, and if you, of course, you have an enormous EDM, unless you do, you wouldn't get a graph this big. But the basic idea is if there's any kind of parity and time reversal violation, as you change the relative phase between the electric field and the magnetic field, you move over between one or the other of these curves. Okay, and so the difference in the population that you measure as a function of this phase shift between the electric and magnetic fields is sort of like the reversals that we're used to in good old EDM experiments. And that plays the role of the knob that allows you to separate out the EDM effect from any kind of magnetic field effects. Because notice, the electric field shouldn't do anything to the system unless there's an EDM. If there's no EDM, if there's no coupling between the spin and the electric fields, then all you get is this magnetic effect. Okay, so that's the key to this whole idea. But there's something even neater than this. If you go back and stare at the Hamiltonian, you'll notice that it's not the electric field that's entering here. It's our good friend zeta, which of course it's a function of the electric field, but it's not necessarily a linear function of the electric field. It's linear in a certain regime, yes, but it is quite nonlinear if you go out of this regime, which means that there's some fun tricks we can play. But the key idea is that the thing that drives the transition from the ground state to the excited state in the presence of parity and time reversal violation is not the electric field, strictly speaking, it's the molecular orientation that's important. And the electric field is just a knob to control the orientation. And so because this thing goes nonlinear, if you drive your system with a large enough electric field, zeta contains lots of harmonics of the electric field. You drive with an electric field at, let's say, omega, but zeta will contain 3 omegas and 5 omegas and all kinds of other odd harmonics. But the thing that matters for the molecule for the EDM measurement is zeta, not electric field, which means you can actually use this 3 omega component contained in zeta. Okay. And so what you can do is you can drive your electric field at a frequency that's different from the magnetic field. You drive your magnetic field on resonance with the hyperfine transition, as usual. Sure. But now you can do this thing where you drive with the electric field at a subharmonic of the resonance frequency, but the nonlinearity in the molecule multiplies that by a factor of 3 for you, and it gives you a zeta that is correctly oscillating at the resonance frequency that you care about, okay, with now thrice the phase shift that you have between the electric field and the magnetic field. Okay? And so there's a bunch of neat knobs of this sort. And so this, we think, is also a nice way to separate out systematics and things that care about electric fields that are linear in electric fields from the effects in the molecule that are nonlinear. All of these are slight extensions of basic ideas that have existed with static EDM experiments, but we just think it's a little bit of fun to play with this technique. And so in summary then, the standard Ramsey technique involves measuring the effect of magnetic fields plus or minus parity and time reversal violation by looking at this latitude angle. This technique that we described involves looking at the same thing, except looking at this in the longitude, with the difference that because there's a zero field splitting, you have to do all of this at some AC frequency, at some frequency omega naught. What's this good for? Well, here's a bunch of things which we think it might be good for. Because you can now stop stressing about comagnetometer states, and because you don't have to worry about finding molecules with any kind of complicated structure, you can imagine trying to do this with some of the kinds of molecules that, for example, Dave DeMille and Timo Fleig described, where the ground states of these molecules don't necessarily have all the bells and whistles that we're used to from molecules like thorium oxide, for example. And if you can work with ultra cold molecules, the promise has always been that you can get very long coherence times and lots of access to other fun tricks like squeezing and so on. In a very general sense, by relaxing these constraints, we think it opens you up to using many more molecules than we would have thought possible for the EDM experiments. And at this point, at least, the more the merrier, I think. Here's an interesting fact. If you look at the magnetic field noise spectrum in any real lab, certainly in my lab, there's horrendous amounts of noise at low frequencies. This is even on a log scale. And then it dies out to very small amounts by the time you get to higher frequencies than certainly kind of megahertz. Okay. And so the interesting thing now is if you ask what range of frequencies this hyperfine transition in this molecule actually cares about, you're driving this transition, and so only a small band of frequencies around this resonance frequency actually matter and will give you linear effects. Okay? And the width of this is basically about 1 over the time for which you do the experiment, the coherence time of the experiment. But what that means is that all this other stuff that's out here, the effects of all of this stuff is quadratic. And so essentially, this is the nice thing about clock states, is that all the DC Zeeman shifts, but when I say DC, I really mean sort of experimentalist DC, which means all the low frequency horrendous stuff that we spend lots of time trying to shield with magnetic shielding. All that stuff gives you quadratic effects. And so it's easier to shield. Working at higher frequencies, this particular band itself is pretty easy to shield using eddy current shielding. And certainly with all of the RF tricks that people have developed over many decades, these are easy to control at this frequency. And then finally, because of the really sort of extreme simplicity of the measurement steps themselves, the fact that you don't have to do any kind of prepare any kind of special superposition of quantum states to make sure that you start off in the right place. That way, you don't have to worry about things like state preparation errors. Certainly, even as a grad student, that was one of the things that kept me worried about the experiment many days and many nights. And so starting with something simple like the ground state can hurt. I've already described to you how the phase of the electric field is a nice knob to have. But if all this is happening at some radio frequency that corresponds to the hyperfine transition frequency, tens of megahertz, that's a beautiful place to control phases with extremely high precision, to control amplitudes with very high precision. And phases have the other advantage that you can smoothly change them from 0 to pi over 2 to pi over anything you like. Unlike DC electric field switches, which require a deep breath and a fond hope that it'll reverse back to the same place that you started from. Okay, so phase shifts and phase reversals are way nicer.
Marius, your time is up.
Okay, great. In that case, I will stop because this is my last slide. Thank you for your attention, and I'm happy to chat and take questions, whether in the next couple of minutes or after.
Yeah, we have a few minutes. Yeah, pretty much. So, John, please ask a question.
Yeah, And thanks for the provocative talk. I was wondering, is there some guarantee that there won't be some other source of nonlinearity in the molecule or in the system that you use to drive it or detect it that won't mimic the 3 omega? I mean, I would be a bit terrified of that. So is there some way to protect you from that?
Jerry, you know as well as I do that there are no guarantees with molecules at all. To the extent that I've been able to think about these things, I can't think of any, certainly for these simple molecules with double-lit sigma structures. But again, if you, the more complicated the molecule, of course, there are lots of ways in which nonlinearities will couple in. But in the paper, which I mentioned right at the beginning, we did go through a bunch of possibilities for systematic effects. All the numbers that I could think of and we put in ended up being not relevant at the kind of, at the 10 to the minus 32 e-centimeter level, certainly. That's not to say that there won't be some horrible thing involving a molecule with 7 atoms attached to it, and that won't come in and bite this. But at least in the simple molecules, everything we've thought of is not an issue. But if you can think of something, please do let me know. I'd love to chat.
So I would like to give question to John Doyle.
Yeah, I'm really getting all the questions from the advisors, aren't I? Yes, John.
Well, this shouldn't be too bad. So as you have done yourself, you've spent a lot of time in your experiments, EDM experiments, kind of controlling the stability of electric and magnetic fields. So just how do I think about that level of constraint, and we'll call it the standard kind of DC application of those fields for doing an EDM experiment? How do those kind of map over to this?
So the thing you would need to control and keep from drifting around is certainly the magnetic field amplitude, right? If the magnetic field amplitude drifts around, your RV frequency drifts around, and then it's a mess. So that needs to be controlled. The electric field strength is not super important. All you're using it for is to try to get some effect. As far as we all know, the effect is 0, and so it doesn't really matter, especially if you're driving to the point where you're saturating the electric field. But even otherwise, I don't really think the electric field will couple in, because it shouldn't really matter except for the presence of an EDM or some parity and time reversal vibration. So I think the crucial thing to control to the level of precision that we're used to from static field experiments is the magnetic field amplitude. And keeping that from drifting around or having systematic shifts with phases, that'll certainly be important.
Okay, next question to Matt Grau.
So with this clock state, you have like first order insensitivity to magnetic fields. If you use like not a clock state, but a field independent pair of states, like an avoided crossing of a magnetic field where you have second order independence, would you get a improved rejection of DC magnetic fields with this?
Sure. I mean, the thing is, you could add as many bells and whistles to this as you want, right? There's nothing preventing you from doing this with a molecule that already has a low magnetic field sensitivity or a molecule that has comagnetometer states. I'm not saying don't use those, but you can certainly add those on to this if you like. All this is saying that the sort of standard thing we've been used to trying to make EDM measurements using these stretch state superpositions, that's not necessarily the only game in town. That's the only point here.
So next question by Paul Gamister.
Hi, very nice talk. A few questions. So the first was along the lines of John's. The time scale that you need to control these fields, is it on the scale that you're doing these phase reversals? Is that the amplitude?
Exactly. That phase reversal is like the E field reversal that we're used to.
And do you have to worry about electric field effects from mixing with the other rotational levels, some sort of differential mixing between
the numbers for that, and it's not super serious, but certainly it's an effect. And depending on the molecule, depending on how far away the rotational states are, if you pick a molecule with the rotational states are really close and you get very strong mixing, then I'd have to go back and check if the numbers are still seem like they'll be easy to control.
Okay. And last question, would it specifically be bad to choose a molecule with a small doublet splitting where you get polarization with really, really small fields?
No, if you can find a doublet, then by all means, you can certainly do it with it. It wouldn't hurt. The thing I'd have to think more carefully about is the following. So in this whole story, there's this plot that comes in, right, which is, strictly speaking, a sort of static electric field amplitude changing. And then, in other words, this is a sort of adiabatic picture, right? Okay. So you're sort of adiabatically changing the electric field and then looking at the orientation of the molecule. That's fine if your hyperfine spacing is small compared to rotational level spacings. But if you get to molecules where the rotational level spacing starts to become comparable to hyperfine, then this adiabatic picture breaks down. And then weirder things can happen. It might still be salvageable, but at least the version that I spelled out works best in the limit when the hyperfine splitting is small compared to typical rotational state splittings.
Cool.
But that's a fairly, that's a fairly decent range of parameters, right? Because typical, at least in the kind of molecules we're thinking about, the hyperfine splittings are tens of megahertz, and rotational state splittings, it's hard to get them to be too much smaller than a couple of gigahertz, for example. So there's still room within which this adiabatic limit is still okay.
I have one question from David, but I think we should start next talk, and then maybe discussion will follow and we can discuss some more about it. So next talk by Gary Gabriels. Okay. Looks good.
You are mute, Zira, in case that you are speaking.
Yeah, we don't hear actually, right? Jerry?
Can you hear me now?
Yes.
Okay, I can't find the unmute button once I shared my screen, so I'm holding my keyboard down. If someone can unmute me, I'll just start rather than distract everybody. So.
Okay.
You can also unshare and then share, unshare, unmute, and then share again.
Helps indeed.
Okay, I think I found the unmute. Can you see my screen?
Yes.
Because it's not advancing now. So I'm clearly having some difficulties that shouldn't be here. Oh, here we go. Okay. I think I'm busy. Okay, you can see now?
Yes.
Okay. It's my privilege to talk today about the ACME EDM experiment, ACME 3 as we call it, and our project is to try and see if we can improve on our previous limit, which is about 10 to the minus 29 e centimeters. We've been privileged to be able to make about a factor of 100 improvement over the last several years, and we're of course doing this, as it's well known in this group, because it's a place where we can look where the standard model and beyond the standard model models can make very different predictions. There are two electron dipole moments, of course, that we know of, and both are important in physics. The initially more familiar one is the magnetic moment, which has been well measured. It's the most precise prediction of the standard model of particle physics. Okay, and at least in Bohr magnetons, and in our group, we've been able to precisely determine it, make the most precise determination of the property of an elementary particle. I'll just note that there is an interesting difference between our measurement and the measurement, the best prediction of the standard model, which involves a measured value of the fine structure constant. There were theoretical papers being generated by this until a new measurement of the fine structure constant from Orsay it disagreed rather pronounced in a pronounced way from the first, and so now it's not known what's going on. But okay, that's the magnetic dipole moment, and that's not the one that we'll talk about today. What we'll talk about today is the electric dipole moment of the electron. And that's, of course, been a major topic in this conference. And the structure of the magnetic moment, having some signed magnitude proportional to the spin, properly normalized, is of course, a perfectly fine way to parameterize the electric dipole moment as well. And many talks have been given, have mentioned why this is interesting, so I'll gloss over that and instead try and focus on what's going on in the experiment. But the big question is, does this exist? It has not yet been detected. Now, P and T violation are required in the standard model, contrary to what the bus in Milwaukee says. Creating an EDM takes no talent, says the bus. It actually takes quite a bit of talent. You've got to do for-loop perturbation theory to couple in enough CP violation to get an electric dipole moment. So this is clearly fake news. And here's the sort of more reputable version of that. But the point of this is that in the standard model, the electric dipole moment is exceedingly small. Now, I put 10 to the minus 44 e centimeters. You can get this up a few orders of magnitude with various indirect methods. But the point is that it's still way smaller than what we've been able to measure. Now, the ACME 1 and ACME 2 and ACME 3 have set these various limits, okay? And the point of my talk today is to show where we are in this process. Here's kind of a historical plot, and here's the two measurements that we've made. After we made our first measurement, then Gilla also made a measurement there. I understand that they're working on getting another measurement which has a comparable accuracy to ours, but that's not yet been reported. Now, the recent EDM history, if we just blow up that log plot, here's the old Berkeley measurement that set the standard in such a laudable way for so many years, the Imperial College. And then here's the blowing up the latest measurements. Here's ACME 1, here's ACME 2, and here's Gilla in between. And the dates are that. So, I mean, there's some years between these. I will note, though, that this, in the history of precision measurements, this has actually been going faster in recent years than what many of us were accustomed to. Now, it constrains new physics at a very high level, 1 to 3 TeV. Particle physicists might say 10 to 30 TeV. I won't go into the detail, but basically we're probing at or even beyond the scale of the LHC for some new particles. For example, if there are some supersymmetric particles on some of these, we're probing well above the LHC limits. There's lots of assumptions in this curve, but the point is that it's a very important and sensitive player in fundamental physics, these measurements. Another way of doing it is lots of people make models and set various limits. And the various measurements that have been done have taken us to the 10 to the minus 29 level. It's getting kind of hard to support these models for reality or limits, and we're trying to go another order of magnitude beyond that. Now, for a measurement, as you all know, we need a huge electric field. So you put an EDM in some effective electric field. Huge is better because the EDM is small. And because you would accelerate the particle, a charged particle out of the apparatus, neutral atoms are what's used. Now, you heard 2 talks ago, you heard about the shift theorem and such things, and so I won't go into that right now. Let's just say that relativistic effects and other effects makes it possible to observe these sorts of effects despite some zeroth order theorems which might first make it seem impossible. Now, molecules have enormous electric fields. Here's the molecules that have been used. This initial paper suggested that our molecule THO, which is radioactive, as was noted a talk or 2 ago, okay, but with a very long lifetime, but not such a long lifetime that we don't have to deal with radiation safety carefully. It's on 100 gigavolts per centimeter. That's a very large electric field. Okay, now over the time, the calculation of this has been refined. There's been some disagreements. Right now, it seems to be about 80 gigavolts per centimeter. Okay, and it's neutron EDM use have to have a very much larger electric field, for example. Now, the THO state that we use, you just heard in the last talk a nice summary of all the things you have to think about when you select a molecule. For me, I'm just going to make it seem very simple and not really go over this. We have a small magnetic moment, but basically there's a level, two levels in the molecule, a metastable state of the molecule. If there is an electric field on and there's an electric dipole moment of the electron, one of these levels will go up and one will go down. Okay, and that's the energy shift that we're looking for. And that signature would tell us that there's an EDM. We do all the standard things where we reverse that electric field either by reversing it in the lab, or we can excite a different pair of states that are almost the same in their properties, in which the internal electric field is oppositely directed to the orienting electric field in the laboratory. So we have lots of systematic checks. Now, the huge electric field still gives a tiny shift, which you can't resolve directly. Okay, it's in the hundreds of microhertz, or if you like, 7 times 10 to the minus 31 TeV. And so we use the standard quantum tricks, make a quantum superposition, let it evolve in time, let the small energy difference that we're interested in, okay, accumulate in the phase. And so that's a kind of amplifier, so to speak, which allows us to see these tiny electric field effects. Now, here's the ACME2 apparatus. There was a ablation source. Okay, there was some rotational cooling to get as many of the ground states we wanted as possible. And then we went into this interaction region. There's 2 glass plates covered with indium tin oxide that make an electric field, and that's the electric field that we reverse. We do excitation of the states that we want in this level using STIRAP lasers, and then we do a detection method here. And all the details of that I'm not really going to go over right now, because I'm going to try and focus on what we're going to do different in ACME3. Here's a more realistic view of some of the electronics and the chamber and that sort of thing. The signal to noise is really good. These are actually observed fringes, and what you'd like to do is you'd like to, as you reverse the electric field, you like to be at the maximal slope location, and we try and do all of that. We can switch these. The most importantly, the electric fields that I was talking about, both the internal electric field direction with respect to the external field and the external field itself. We can reverse these relatively rapidly, but we do many more switches than that. Change the light polarization a little bit and so on. And so, but again, that's all part of ACME2. I'm not going to go through that right now. As we go to ACME3, I'm getting an order of magnitude when you already have achieved 2 is a little challenging sometimes. Okay, and so let me refer you to the shot noise limit formula. This is the uncertainty in the electric dipole moment, and importantly, it goes inversely with the coherence time. This is the time that the particle evolves in this superposition quantum state. And it goes as the square root of the number of molecules, or the rate that you produce these molecules. It's the same for a given time. And so basically, these are the two things. We can't really change the electric field, okay? And life sort of sets the time scale. So these are the two things we'd like to improve. Here's the ACME3 team. It's David DeMille's group at the University of Chicago, John Doyle's group at Harvard, and mine at the Center for Fundamental Physics at Northwestern. Here's some of the participants. And the one thing that might be interesting to some of you, ACME3 is actually being set up at Northwestern University. Our previous generations happened at Harvard. That's a natural evolution because I moved to Northwestern and Dave moved to University of Chicago. And so the experiment is going to be closer to some of us. So. Okay, that's all being set up right now. We have a lab, it's cleared out, and we're assembling apparatus. Now, let's go now into more details about what sort of improvements we can expect. The first thing I'll mention is that the thorium monoxide lifetime, actually I should say the H state, the metastable state that we use for the experiment, which we had thought was at least 1 millisecond, turns out to be 5 milliseconds long. That's a fairly big deal because in the shot noise formula, that gives us a longer coherence time, and the coherence time comes in as the directly, not as the square root. So that's good. On the other hand, that good news is tempered a little bit because if you increase your interaction region from 20 centimeters to a meter to take advantage of this, basically there's also still a 1/e decay time, okay? And so you don't really get the full factor of 5, but you'd like to get as much as you can. Now, I was saying a factor of 5, we've been trying to measure the lifetime. Well, we have measured it well enough to design a new apparatus. It's roughly 4.6, but plus or minus a 9 in the last digit. This uncertainty is still under discussion. Exciting a beam of molecules with different laser optics at different points is fraught with some systematic challenges, and we're still working through that. But we know this well enough for sure. Don't take the uncertainty too seriously yet, but we know this well enough to design an apparatus which is much bigger. So the ACME2 experiment had 5 cylindrical mu metal shields around it. Here was its interaction region. The ACME3 interaction region is quite a bit bigger. Okay, and we're trying to drop down to 3 magnetic shields. The shielding material is incredibly expensive, and we're trying to keep the physical size manageable. The projected ACME3 advances, I've already talked about one now, and that is the increased precession time. That's, again, this circled tau here, which I've already pointed out. You don't get the full factor of 5 because you have an increased decay time if you move further down beam to do your detection. In order to realize this, of course, we need this bigger magnetic shield region I've already told you about. Here's some calculations of the shielding factor that we're trying to get, and we've been doing finite element analysis calculations of that. Finite element analysis is wonderful stuff, but it has the danger that if you do it, some people don't think you need to do an experiment, but okay, we're trying to avoid that. We're right now, the idea is that we're going to make a rectangular shield, unlike our previous cylindrical shields, and we're going to be able to drop down the various layers on top of the 3 layers on top of the chamber, and that's going on. Again, we had to calculate the vibration analysis. I love this picture. It may be slightly exaggerated as far as the vibration, but you can do this, not so much in the lab, but we don't have engineers, so we do what we can. So we're trying to get lower magnetic fields, but using less magnetic shielding material. Now we're aiming for on the order of a microgauss now and a microgauss gradients. In ACME 2, we had the problem that as time passed, we developed 100 microgauss field within our chamber, and that was enough, we think, and we tried to carefully check for systematics that didn't cause us problems. We're not so sure that it wouldn't cause us problem when we improve by a factor of 10 in accuracy, so we're paying more attention to shield design and degaussing. And the other thing is we've designed an active cosine theta coil. This idea, well, to me, it came because when we make solenoids, there's something called active shielding, where if you take a solenoid and you make a solenoid inside of the solenoid and it points the wrong direction, you reduce the magnetic field you make, but you can cancel the exterior multiples. And so we're trying to do that sort of thing here to keep the magnetic field that we produce inside of our apparatus from magnetizing our magnetic shields from the inside. Okay, and it works on paper. We'll see if it works in practice. Another challenge that we're trying to face with the larger size is we're making our field plates and yet having glass coated with indium tin oxide that doesn't absorb and give us birefringence in the plates is a bigger challenge. That's an ongoing project right now that we very much hope is going to work out, but that's a development that's underway. The other projected ACME 3 advance, is trying to improve on the square root of n, okay? And so we're getting signal gains in various ways, okay? There's an electrostatic lens that's pretty exciting, that's now working, okay? There's a CIPM detector upgrade, and there's some improved collection optics, and there's some timing jitter noise reduction. There's maybe a little better rotational cooling too that didn't make it to this table. But let me talk about the electrostatic lens because that's a pretty big deal. What we're doing is inserting a hexapole lens here, okay, so that the molecules which tend to want to come out in all directions here, okay, or in a broad swath of directions, we can focus them back into between our field plates, and that's important for getting more molecules. It's also important for taking advantage of the longer lifetime. So those two things together are really critical. Now, to the end of seeing if we could do this, we explored the properties of another state in our molecule, the Q state. There's a paper about that. It has a lot of nice properties, but the long and the short of it is, with reasonable electric fields, you can get enough polarization to actually steer the molecules. Okay, and so here's basically this is just showing roughly down the axis view, plus and minus 8 kilovolts is what we're trying to put on these bars. Some of you may know that when we experimented with this some years ago, we found ourselves making X-rays. So you have to be careful with this, but I'm happy to say that that doesn't seem to be a problem in the current version. The hexapole lens, here's the first signal we saw not so long ago, okay? And right at the exit of this lens, there's a picture of the inner guts. We had a factor of 2.5 bigger signal with the lens on compared to off, but that's not the whole story, okay? Because the lens is actually designed not to focus where we looked so far. It's designed to focus further downstream, and so we think we're going to have, with a longer lifetime, we're going to have, and this focusing, we're going to have a much bigger effect here because we're actually not. This isn't where we do our experiment. We do it a couple of meters downstream. Okay, so this electrostatic lens, it's worth saying that it's hard to decouple the lifetime and the electrostatic lens. It's important that if we didn't have the lens, we couldn't actually make an apparatus where the molecules didn't spread out so much they'd hit our field plates, and you just can't make the apparatus arbitrarily large. Okay, and so if you put all of these factors together, you take the square root of the flux enhancements, and you take the direct lifetime estimate, it gives you a factor of about a factor of 32. Now, if you see different of us give the talk, it might vary from 30 to 31, or I think most of us agree that this is a way to write. We hope to get a factor of 10 better, okay, from these sorts of effects, okay? Now, if we would get this number, this would bring us to this limit, but I scratched it out right on the slide. That's just a speculation of where we hope we maybe could get in the best possible case, but no measurement has been made, so no one should certainly quote this number in any way. Okay, the summary is for the electron-electric dipole, we've had 2 10-fold, 12-fold improved measurements. No electron EDM has yet appeared. We're probing for new physics at TeV scales and higher, comparable or higher to the LHC, very much higher in some cases. And a substantial improvement, meaning a factor of 10, seems possible. And we're very busy at work trying to do that. We hope that maybe we could get a result in the next, say, 3 years. But of course, as you improve the sensitivity this much, one can always encounter some sort of systematic effect that might take longer to disentangle, and no systematic effects really have been studied at this point. So I think the prospects are very bright here, but it's going to take a lot of tenacity and hard work and some time before we realize these goals.
Oh, thank you so much. Very interesting talk. So we have question now time. Any questions?
Oh, that's good. Nobody doubts that we can do this.
Yeah, no, there are questions. So
No, there are questions, Ronald.
Yeah. So yeah, no, just if you can say a bit more about the second delta state that you found. So that has a very long lifetime, right?
Yes, I think I listed the properties of it. I don't remember them from memory, so I'll scroll.
Yeah, you listed that. I saw like 60, but yeah, you can comment. Are you planning to use that in the future, that second delta state?
No, we're still going to use the H state for our current measurements. Okay, so that plan is not going to change. Mm-hmm.
Okay.
So next question, Paul Gamilton.
Very nice talk. So one thing that was interesting to me was this being able to do the shielding with less shields, and also reduce the polarization on the shields as well. Will you guys have a write-up on that, or can you say more about the plan? Because it seems generally useful. I know Hunter, for example, would love to have something like that.
Well, yeah, we probably should succeed at it first, but so far what we've been able to do in simulations, it seems like it's doable, okay? But I think that and we're hopeful that at least some of the problems that we had in the past was due to our internal magnetic field, which was changing all the time and messing with the polarization of our shields, so that even though we degaussed our shields as part of our cycle, that it wasn't adequate. I can't really tell you exactly which part of the process is going to improve it. We think this should be possible, though, based on what others have seen and the experience of people making shielded rooms and so forth. And we're trying to use some of those technologies. Of course, what's different in the shields that we're building is, unlike shielded rooms, you have the need to occasionally tear into things and take the apparatus apart and put it back together. So we've made the shields, not just bolted together once for all time. So, but we certainly will try and write that up once we get this demonstrated. Mm-hmm.
Okay, we have this Xing Wu. Next question.
Hi, it's not a question, just try to answer Rona's question about the second delta state. So that state, so it turns out that the electron spin is perpendicular to the molecular axis, so it's not sensitive to EDM, but we are using it to do the lensing and possibly do a co-magnetometer measurement with it.
Mm-hmm. Yeah, but we'll still stick with the H state for the actual EDM measurement. That's right. Mm-hmm.
Just waiting for some more questions.
Well, while there's a lag, Xing Wu is a postdoc who took the lead on the making the lens work, and he would make an excellent faculty member. How do you like the way I slipped that in? So, yeah.
Yeah, if there are no more questions, I will say a few comments. Yeah, excellent jobs. I think the ACME has been a very strong example for our community. So it's been really, the success of ACME is somehow helping us to grow. So, yeah. So we wish you guys to continue as the way that you are doing.
Yeah.
So yeah, we can come back at 2 p.m. So if the speakers have time, so I suggest you to go to 2 different breakout rooms, and then people can ask more questions for 10 minutes or so. And then we can just come back at 2 p.m.
Thank you for your kind words about ACME. The one thing this community can do is continue to send us good students. So.
Okay.
So yeah, Amar, if you can go to room 1, and Gerald to room 2.
I'll do that.
Yeah, super.
Will we meet at room 10?
Yeah, today I will be busy during lunch, Timur. So, but yeah, we can meet later today. That's okay. Yeah, I can send you an email. Yeah.
Okay. Yeah.
Yeah. Gerard, can you join breakout room 1? I think only 2 speakers. I think we can just join the same room.
Okay.
Heini, can you hear me?
Yes.
Okay, super. So we are like 1 minute to 2. While people are joining, I will play a video that our summer students and PhD students made during the week. So I will share this. So let me see, share computer zone.
We overlap the isotopes with lasers.
Play me with some bass and drums, cause I'm about to go crazy dumb. Pay me some attention and I'll educate your cranium. Crystals, yeah, we're laser numb, sapphire and titanium. But wait, I'm out of order, so let's start it at the target. We irradiate uranium, and some decays to radium. In jet fluorine, we're making some radium monofluoride molecules. They're pretty hot and they gotta be cooled. Prior to use the spectroscopy tool, apply a strong field and they follow the rule. They're energized with the ionized tool. Follow my drift if you have left school. If not, don't sweat it, don't matter, my dude. I can't break down kinematics for you. 40 kV make the cations move. Yeah, that's electrostatic extraction. Next we filter, then we trap them, flapping quadrupole attraction. If all trap, we buffer gas them, and that causes cool reactions. The ions are not static, scatter non-adiabatic, so the cooling's automatic. Yeah, it's quite a useful tactic. Helium gas collisions induce a few transitions, reducing our partition function, thus upping precision. Next we're on to the charge exchange. Gotta change my flow, make the bars insane, so the beat pass through a sodium vapor. RAF, an electron taker. Neutral molecules exit the chamber, deflect the rest like see y'all later. Now we're back to the TISAP laser, scanning wave number and logging the data. I get state of annihilator, level structure interrogator, cause molecules are resonators, responding to strong oscillators. See figure 1 from our paper in Nature. Next we pulse with a 355 nanometer light, re-ionized only if we already excite ground state sigma to A2 pi, or a higher lying state if the scan laser resonates. Ions are detected once deflected to collection plate, tweaking the frequency, seeking some evidence, seeing a peak when we sweep through a resonance. Technique is elegant, tweaking intelligence, speaking out beats, I'm a geek in my element. Check it. Alright, we've covered methods. Let's focus on results and goals. First of all, we had to probe positions of the manifolds for vibration normal modes, plus Frank Condon factors, so we know if we could trap and slow gamma damp molasses cold. I'm talking laser cooling, if that wasn't understandable. It's important for precision measurements on things like anipodes and other such moments that don't consider parity, plus deviation from king linearity, time reverse breaking, comparing polarities, find such a constant to track regularity. Unstable isotopes reproduce scarcely some of these signatures, enhanced apparently from certain structural irregularities like deformations of large angularity. Got all that? Alright. Molecules, they magnify permanent dipole moments, plus they have more transitions to measure isotope shifts and isolate components that are higher than the lowest order terms of standard model effects. Count for them all, then what do you get? Well, if you are left with signal excess, it could be a sign of 17x or other dark bosonic coupling strength. Axion field, your shot I will check. Shout out to Buletich, with whom we're doing this tangle state measurement technique is ludicrous, though we are new to this method as used to quantum computing with trapped ion qubits.
We call this kind of flow a super flow.
And the fruits of all our science could have practical appliance, like nuclear optical clocks to keep time with, and a smorgasbord of tactics yielding ultra narrow line widths. We keep climbing ever higher, standing on the backs of giants. With that effort been at triumph, looking for PT, we'll find it. Then our paper, we would write it, and then you should probably cite it. Oh my bad, I got excited. I'm just saying, future's bright and all the factors in alignment. That's a wrap. Hope you liked it.
I hope you like it, the video. So the good thing is, what's impressed was bachelors and students in one PhD, and they made it in a few days. So that's a lot of merit. Yeah, good. So yeah, thank you, Alex. By the way, Alex, are you around? So I hope that you were. He is not. Okay. Yeah, we'll post that on the webpage. Good. So I think this highlight one of the things that I like of the community, that the most important is to have fun. And I always said I only look for fun collaborators. So, and I see a few faces here. So it's a pity that I cannot have you at Boston, otherwise we'll have a lot of fun. So, and my collaborators know. So Jason can say that once he ended in Colombia one weekend, yeah. Good. So the plan now that we are here is to discuss how we keep ourselves as a community. So during the week, we were discussing several panels where we have very interesting discussions. So I will take Alex out. And so let me just come back to this. And the plan today is not to discuss independently, but an open discussion with all of you and go step by step for these different topics. So as a reminder, there were 4 different panels, one focusing science impact, right? Kind of trying to identify their main experiments that should motivate the community. So the needs that we need from the different theoretical developments, that was panel 2, although they are very much connected, all of them. And another aspect that I like very much of this community is that it really requires a very strong collaboration between experiments and theories in 3 different fields, right? High energy physics, nuclear physics, and molecular physics. And now with radioactive ions, we also need very much the chemistries, right? And even condensed matter. So it's really an interdisciplinary community, and I hope this actually make this more rich, this community, and open more opportunities. And we saw even some examples for astrophysics and so on. So the other one is this kind of experiments have been, I will say, in a great part motivated by the success of the experiments with the stable molecules, right? Like the standard, starting with standards, so terbium fluoride, hafnium fluoride plus, and of course, the ACME collaboration, thorium oxide. So we really need you guys to grow in this community. So we are mainly learning from you. So we expect to combine these challenges with the challenges that we face in radioactive beam facilities. So one thing is clear, we cannot progress alone. So it really needs your support. And the last, but one of the most important points is that we need to continue as a community, and we need to support each other strongly, right? There is a need to do not only one experiment, but many experiments, right? So it has to be clear that there is not a single experiment that will solve the questions that we need to solve. So there is a real need of many experiments. And actually, there are opportunities for many of them, right? And it's not that we are constraining a small region of the phase space. So we really need at least 2 experiments constraining the same region. So we really need more experiments. Okay, so let me go to the discussions that we have in the first panel, science impact. I will summarize some of the ideas, but please feel free to contribute to that. I will put in the chat, I already did, but for those that maybe didn't get the chat, let me see if I can do this. I will have to stop. So in the chat, I add in a Google document where we are summarizing these ideas. Feel free to modify that. Be sure that you put what you want to see there, okay? So the idea is to really support all of you. So, but to do that, you need to say the ideas. You need to put your voice. So the panel was coordinated by the names that appear here, but we have input from different people. So we identify 4 main fields in which we can contribute with radioactive molecules. Something that is quite clear is fundamental symmetries and the search for neon physics. This is kind of our big umbrella, and it's a main motivation. But also there were topics in nuclear structure that I personally am very interested in, and it's also a great community, and there is a need of nuclear theory. So this is a kind of a very good way to join efforts with this community. Okay, this will be, all of those, or let's say all of these topics are strongly correlated. Quantum chemistry, of course, so it's very important. So yeah, we can contribute to the progress of quantum chemistry. and astrophysics, we saw some examples, some interesting example in which radioactive molecules could do a unique contribution. So there are different topics here, right? I will go quickly through them. So there is a very well motivated effort to study PT violation, right? It's a very simple question. So the matter-antimatter asymmetry, right? So EDMs in general are very well motivated. Hadronic parity violation, we know it's very important, right? But it requires nuclear theory. Nuclear theory is essential here to do any, or to kind of highlight the motivations of this work. Although it has a strong motivation, right? Low energy test of the standard model, constraints to NEOC bosons, and some open questions here. We can contribute to other fields, but to get to this motivation, we need the stable nuclear theory. So we are very happy to see the theory progress in this, and you guys will be central in these developments. So then we made some recommendations. So some recommendations were organized as follow. I will just read a few then, and then I will be jumping between the topics. So because I say the need of nuclear theory, so it was highlighted that also theories need support, right? And one idea to support that will be strongly suggesting adding theory collaborators in experimental grants, okay? So we will try to do as much as we can. And I think this, many times experimental grants are larger than the theory grants for obvious reasons. So perhaps adding a small fluctuation will also help and motivate the community. So that was one suggestion in this direction. So the experiments that kind of will guide those developments from the developments in theory are the line nuclei that now can be reached with ab initio nuclear theory, but now they are going into the heavy region like Jason and Takayuki presented. It was said that around plus minus 1 nucleon in closed shells and isotopic change will give us a good understanding of this phenomenon. And let me know if there are cases of particular interest. So we were adding a list here. There was some molecules that we saw during the workshop. These are just a few, right? Please be sure that you add the molecule that you would like to study or the atom that you would like to study here. And there are some kind of highlights for Anapole moment with some justified ideas. So we will expand a bit more about that. So then the recommendations. One is that we should put all of these ideas, and this is touched in panel 4 that is working in a white paper. And since we have our editor-in-chief of Journal Physics G present, so we have the strong support to publish these ideas in Journal Physics G, which will reach the nuclear and particle physics community. And I think that this is a great idea and a good opportunity, and the field is quite exciting that we should do it. So it's important to highlight the discovery potential and complementarity to colliders. So we have to educate the high energy community. So many times the support is a bit skeptical just because they don't understand what we are doing. And in my opinion, it's important to say that we will not take their job, right? It's highly complementary, right? We should never say that this is better than LHC. We should say that it's highly complementary to colliders. So theory needs support. I already commented that. And we need a close collaboration and a close combination of expertise to be sure that we are moving in the right direction, right? So we should be sure that we don't overlook results from our communities. With this, I mean that we should invite also particle physicists to join our communities and nuclear theorists and all representatives from the different fields in this kind of vision that we are organized. Okay, with that, I will stop speaking, and I would like to hear your ideas, your opinions, and what do you think? So I have one, I will stop sharing. So Amar, will you take notes Please, is Amar present?
Yeah, I'm here. But
Okay, thank you very much, Amar. So let me see, I'm trying to see my chat. Okay, John Burr, yeah, please.
Hey, I don't think you mentioned magnetic quadrupole moments. And I had two questions about those. One, we've been told in the past, I don't know, the literature seems to say that they're much easier to calculate than the shift moments. You don't have the cancellation that's inherent there. And it's a magnetic phenomenon in the end, so you don't have screening of the atom. But I would ask, does that really hold for the whole calculation? To me, it's an eye opener to see the very detailed Dobzhansky Engel, et cetera, paper that had a very big difficulty with the nuclear matrix element part, and that's not at all under control. And although the octupole deformed part is kind of under control in some sense. So is there a similar nuclear matrix element or expectation value you have to calculate with some interactions in the magnetic quadrupole moment that hasn't been considered yet? Is there going to be a complication there, theoretically?
I think it's the same. There's always these
Same?
VPT, which allows you to have a moment.
Is the same sigma dot r effective one body operator?
For that VPT, yeah.
Yeah. Okay. So that's annoying and sad. Okay. Well then fix it, please. It'd be awesome. We'll try to help us find. We'll try to help find observables to benchmark it. That would be great too. Yeah, that's good to know, John. It's also very hard experimentally. The experimentalists will tell you, I'm sure, that you get the coherence times you need in systems with unpaired electrons in the atom. That's a big difficulty with the magnetic quadrupole moment. But yeah, okay. I think it should be on your list of things to measure, though, in this thing. I mean, Nick's doing this in a terbium hydroxide, right?
Right.
And just because it's not radioactive, it's still a good thing to measure.